let's begin. Anne, it's yours.
Okay, thanks, Jerry. So one aspect that Jerry didn't mention is that all the presentations this morning are 12 minutes, followed by 2 to 3 minutes of questions. So I will remind the speaker after 10 minutes. So there's 7 talks in this session before the coffee break, and 5 of the 7 taking data at the LHC experiments at CERN. Then we have our MUMA experiment close to a nuclear reactor in Belgium, and we have a presentation from Bell in Tsukuba, Japan. So I'm pleased to introduce the first speaker today, Caroline Strasser from the University of Namur in Belgium. Caroline will be introducing the MUMA experiment. It's designed to search for neutron interbrain transitions in the context of brain world scenarios. And Caroline will share their first results and their perspectives for the future. Okay, so thank you, Caroline.
Good morning,
you can
everyone.
Share your slides. Good morning.
I will share my slide. Yes.
Caroline, I will remind you after 10 minutes. Yeah.
Okay, thank you. Thank you and good morning, everyone. Today I will begin this morning session by thinking about the MUMA experiment. I will begin by introducing and speaking about the context of the research. The general context of this research is based on the idea of an hidden sector. An hidden sector is an extension of both the standard model of particles and the lambda CDM cosmological model. And the purpose of such hypothesis is to address some shortcomings as, for example, questions of dark matter and dark energy. The hidden sector can take 2 different forms. The first one is a duplication of the standard model content. And in this context, each particle of the standard model has mirror partners, which is sterile. And the second form of the hidden sector is a more geometrical meaning, and it is the brain world hypothesis. The brain world hypothesis is the idea that our universe is for space-time hypersurface embedded in hyperspace, what we call also a bulk, which is a universe with more than 4 space-time dimensions. And so it requires the existence of extra dimensions. And during this presentation, I will focus on a subclass of hidden sector models. And in this subclass, fermions could exist in both the visible and the hidden states. And in particular, a neutron could have a sterile hidden state, and a mixing could exist between the 2 states and lead to visible hidden neutron transitions. And thanks to this phenomenon, we could constrain brain world models. Brain world models are often considered in the literature. And in 2010, it was shown that neutrons could undergo fast oscillations between 2 brain worlds. So in particular, if we have a visible neutron here in our universe or in our visible states, it could leap from our brain, reach another one in the bulk, becoming what we call a hidden neutron with a probability P. And after that, these hidden neutrons could come back into our visible state or visible universe with the same probability. And this probability is proportional to G squared, and G is here the coupling constant between the 2 states. And so here we can, thanks to that, it leads to a new phenomenological way to probe brain world scenarios with such a transition. And here the parameter of interest is G, the coupling constant. And G is proportional to the square of the mass of the particle, here a quark, for example. And it is also inversely proportional to the energy scale of the brain. And the energy scale of the brain is related to Xi, and Xi is in fact related to the thickness of the brain world in comparison with an extra dimension. We don't know the energy scale of the brain, if it exists, but it could be at the TAFE scale, but it could be also at the Planck scale. And the idea here is even if the energy scale of the brain is at the Planck scale, G can reach accessible values for low noise experiments. Such experiments are called neutron passing through wall experiment, and I will focus on it just now. The disappearance of a visible neutron into an hidden brain world could be induced thanks to nuclei with high elastic cross-section. The cross-section of transformation of a visible neutron into an hidden one, thanks to such a nucleus, is proportional to the elastic cross-section, the usual elastic cross-section of the nucleus, and also proportional to P, the swapping probability of the neutron. And the reverse process is also possible, so we can induce the reappearance of a hidden neutron into a visible one thanks to the same kind of nucleus. And thanks to that, to this phenomenon, which could be possible, we could propose this kind of experiment setup. And we propose this kind of experiment setup, which is made of several elements. The first element is a high neutron flux, because the phenomenon is very rare, so we need a lot of scatterings. The second element is a converter, and which is made of nuclei with high elastic cross-section. And this converter could transform a certain proportion of the neutron flux into an hidden neutron flux. And for example, the two first elements here could be a nuclear reactor. The nuclear reactor will provide the high neutron flux, and the moderator of the reactor acts as a converter. The central element of such experiment is what we call a wall, but it is in fact a shielding. And the role of this shielding is to isolate the rest of the experiment from the visible neutrons background. Just after the wall, so the hidden neutron flux can pass through the wall because it is not in our state. And just after the wall, we have the regenerator, which is also made of nuclei with high elastic cross-section. And it is, if the phenomenon is possible, the regenerator will regenerate a certain part of the hidden neutron flux into a visible neutron flux to be detected thanks to a neutron detector here. And as you can see here, the expression of the hidden neutron flux, which is given here, is proportional to the swapping probability P. I will come back on the swapping probability P just after, but it is very small. And the neutron rate regenerated by the regenerator is also proportional to P. So at the end, we have something which is proportional to P squared. And the idea with such experiments is to, if we consider a nuclear reactor, is to make measurements during cycle of the core, and also measurement during shutdown period of the core, and see if we have some extra signal during the cycle of the core. And if we have such extra signal, it could be lead to a new physics. That's the idea. And here at the IL in 2015, an experiment like this has been carried out. And in this experiment, the regenerator was in fact a detector. And it was an helium-3 proportional counter. And this experiment made possible to find this constraint on the neutron swapping probability P. And as you can see, it is very small. And here I will focus on a new experiment that we call Murmur, which is an improved detector placed for the moment near the BR2 nuclear core at Mol in Belgium. And it's also a collaboration. And the aim of this collaboration is to constrain brainware cosmological scenarios thanks to the Murmur measurements. And the major improvements of this experiment is a noise subtraction thanks to measurements made during shutdown and cycle periods of the core, and also a regenerator which is now separated from the detector and which is made of 50 kilograms of lead. And we have also a better noise discrimination. Now I will describe the murmur detector. So here we have a complete view and a sectional view. The neutron detector is here. It's an helium-3 proportional counter. And the neutron detector is surrounded by lead, a block of lead. And lead is the regenerator. And the whole is surrounded by a shielding, which is a boron carbene shielding. We have here all the dimensions of the experiment. And at the top of the detector, we have a plastic scintillator, which acts as a veto, because muons could directly inside the lead induce fast neutrons due to spallation, and which is obviously a source of background for us. The experiment is just here, near the BR2 nuclear core, which produce the high neutron flux. And the moderator of the core is a matrix of beryllium, which acts as converter for us. And at the beginning of this experiment, we have an extra signal during cycle of the core, but it was simply due to fast neutrons, which was not completely stopped by the shielding in boron carbide. So we added an extra shielding here in green, which is paraffin, between the core and murmur. And thanks to this extra shielding,
Caroline, you have 2 more minutes. Yeah.
Okay, thank you.
Thanks.
And thanks to the extra signal, we didn't measure extra signals. So thanks to these measurements, we can put a new constraint on the swapping probability. And I will finish by the first result of this experiment. So we can find this constraint on the neutron rate in the detector, which is better than a factor 4 than the previous experiment at the ILL. And thanks to these measurements, and also thanks to some simulations, we can find a new constraint on the swapping probability P here. And as you can see, it is better than the previous constraint, but it is also not far better. And it is explained by the fact that the BR2 efficiency to produce hidden neutrons is weaker than at the IL by a factor 7. But thanks to the lead as a regenerator, and also thanks to the noise subtraction, it makes possible to give a similar constraint than the previous one. And thanks to this kind of measurement, we can constrain brainward scenario and rule out a certain range of parameters. That's the idea behind. And I will finish by some perspectives. Some improvements of the experimental setup are planned, as for example, the addition of shielding, extra shieldings, boron, cadmium, and polyethylene, and also the addition of plastic scintillators by the side of the experiment in order to mitigate the neutrons background due to muons in the matrix of lead. And why not the test of the detector near the nuclear core of the ILL in order to beneficiate of their high neutron flux. Yes, that's all. And I thank you very much. And I also thank you, the organizer, to give me the opportunity to give this talk. I don't have a Zoom room. I don't know why it's...
Okay. Thanks very much, Caroline. Merci. Okay, super. Thanks for sharing that. Are there any questions for Caroline?
Maybe I would like to ask if I can, what is the neutron flux that you have from the reactor?
Sorry, neutron flux?
Sorry, from the reactor, what is the neutron flux?
Yes, it is 10 exponent 15 neutrons by centimeter square and second.
Okay, thanks. And the second question, is this P, the probability, somehow dependent on the energy of the neutron?
We use here thermal neutron, but it is not related to the energy. So, but the calculation was made for the moment for neutron which have a low energy. But it could be also the case with high energy neutron. So, but for the moment, we only use thermal neutron because it is easier for the moment for us to do the calculations.
Okay, thanks.
with scintillator, you will also read out those scintillators.
Sorry? I don't hear you.
Sorry, my connection seems to be unstable. Okay, you hear me now?
Yeah.
Okay, if you go to your Outlook, to your perspectives.
Yeah.
On the addition of the plastic scintillators to the sides of the experiment, you will measure the amount of background from muons as well. You will instrument those scintillators. Yeah.
It is an anti-coincidence system. So when we measure muons in the scintillator, the neutron detected in the helium-3 detector are suppressed from our data.
Okay, great. Thank you very much.
Thank you.
Okay, so I think more questions can go to the Mattermost channel. And I'd like to introduce our next speaker. Caroline, you can stop sharing. Super. Okay, so our next speaker, I could call him a Czech local, Benedikt Bergman from the Institute of Experiment and Applied Physics in Prague, Czech Technical University in Prague. And Benedikt will present for us TIMEPICS-3 as a solid state time projection chamber in particle and nuclear physics, and give us also some applications. Okay, thank you, Benedikt.
Okay, thank you very much for the introduction. So as already said, I will describe the TIMEPICS-3 and how it can be used as solid state time projection chamber. I'm not sure if I will have time for some applications in particle and nuclear physics, but I put it in some additional slides. So if you are interested, you can have a look at the slides and contact me through the chat. Okay, so the main protagonist of my talk is the TIMEPICS-3 detector. It was developed in the MEDIPICS collaboration at CERN. And it basically consists of 256 by 256 pixels with a pixel pitch of 55 microns. So since it's a hybrid pixel detector, you can have different sensor materials with the same readout ASIC. And the most typical materials which are used is silicon, cadmium telluride or cadmium zinc telluride, and gallium arsenide. I will show some results later from silicon and from cadmium telluride. The features of this chip are that it features a data-driven readout scheme, which means that only the pixel which sees some event is read out, all other pixels stay active. And this scheme can be used up to 40 megahits per square centimeters and second. Moreover, in each pixel, we can measure simultaneously the energy, which is the TOT, and the time in each pixel. And what is most important for this work which I'm presenting is that we have a time resolution around 2 nanoseconds or better than 2 nanoseconds, which finally allows to measure the drift times of charge carriers in the sensor layers. So to reconstruct the particle trajectories in 3D, we use a similar principle as it is used in time projection chambers. But whereas time projection chambers are gas-filled, we have a semiconductor device, which means we actually profit from the speed of operation and also from a higher stopping power. So if we have an ionizing particle passing through the sensor layer, you will create electrons and holes in the depleted area. And these charge carriers finally start to drift through the sensor layer, so that depending on interaction depth, the signal at the pixels is induced at different times. In order to understand this process, we had a look at the charge carrier drift motion, which is described by the equations given here. So the drift velocity is given by the charge carrier mobility times the electric field. As I said, I used silicon and cadmium telluride detectors. So for silicon, the electric field in the Z direction is assumed to be linear in Z. And for the cadmium telluride, I simply use kind of constant. Second thing which we should understand is the kind of small pixel effect. So if we look at the Ramos theorem, it tells you that the induced charge at the pixel is given by the difference in the waiting potential from the start point and the end point of the charge carrier times its charge, of course. And here is the waiting potential for exemplary for a 2 millimeter thick sensor with 55 micron pixel pitch. And what you should see here is that the highest signal is created if the charge carriers have passed through the whole sensor and are close to the pixel side. Using these equations, I could do a kind of numerical simulation and create lookup table which link the measured timestamp and the measured energy to the interaction depth set. For more information, I would recommend to have a look at these papers here, or also to contact me. I can explain it. To check if this works as expected, we have done some measurements at the SPS at CERN and also just in our lab with cosmic muons. And we had pion beams of 120 GeV and 40 GeV. And the experimental setup is shown here on the picture. So we have the Timepix-3, and it is irradiated by a pion beam at an angle of 60 degrees. If you look at the output of the data, it looks in the 2D projections, which we get. We have the time over threshold, so the energy information, which is shown here on the left. And we have the drift time information on the right. And what you can also already see from this drift time is that with increasing distance to the set, you get higher drift time measurements. And these results are for 500 micrometer 6 silicon sensor. Now using the methodology described, I could do the reconstruction of these tracks in 3D. I show some example of the pion tracks here on the left. So you see pion tracks, and I selected the ones which had long outgoing delta rays. And since I knew what was the angle of impact of the pions, we could also estimate the set resolution, which was around 30 micrometer. And we could see how well the drift time model describes the reality. And here we found out that there is a systematic uncertainty present, which is in the order of 25 micrometers. Here on the right is an example of a cosmic muon, which is measured in our lab. So I did a 3D fit to the reconstructed track. And then you can look at the deviation of the measured points to the fit, and you can see that this is described by a Gaussian with a sigma of around 55 micrometers. This indicates kind of the precision you can get in 3D for each point. In the second measurement, we used a thicker detector, so a 2 millimeter thick cadmium telluride sensor. And this time the pion beam energy was 40 GeV. With cadmium telluride, things are not as easy as with the silicon, because you also have charge scoliosis due to incomplete charge collection. So we had to correct this. But luckily, since we measured the set coordinate and the charge collection efficiency simply depends on set, it was possible to correct this. With this 2 millimeter thick cadmium telluride detector, we were able to achieve a set resolution of 60 micrometers. To separate the pion tracks from delta rays, we use this half-line detection or half-line transformation. So we get the track length, and then we can easily calculate the stopping power by energy divided by track length and the density of the cadmium telluride. So this half-line result is shown here with the blue lines. If you look at the data from the test beam, we do not only see pions, but we can also see other particles. So here is an example of what I call electron-positron-like events, which could be, for example, due to gamma rays interacting in the cadmium telluride detector, creating Compton electrons or photoelectrons, which I would say is the upper left one here, or some electrons which are created in front of the sensor, which pass completely through. Or here on the right, what I would think is pair production. So you have electron-positron pair created in the sensor layer. And the last event category to show is my favorite one. So we found a fragmentation event. So a particle interacting in the sensor induces a breakup of the nucleus so that you can see a kind of shower of secondary particles. Okay, so now I have described methodology and shown some tracks we can measure, but what is it used for? So I put here a list of applications where I think it's very useful, or which are kind of it's a very, very subjective list. So probably there are more applications which can profit from this. And I would like to start with the single layer Compton camera. So this was a nice work which was described by one colleague from our spin-off company. So especially this cadmium telluride detector can be used in the kind of Compton camera setup to localize gamma radiation sources. Moreover, it was shown that with Timepix detectors, you can measure secondary particles during hadron therapy, and that you can even reconstruct the Bragg peak position from this measurement. Timepix detectors, since they are rather lightweight and small and also don't need so much power, They are also very good instrument for the use in space. So for example, for space weather analysis. And the most prominent example here is the SATRAM device, which measures the electrons and protons, which are trapped in the Van Allen radiation belts. Of course, if we fly in this low Earth orbit, we also see particles from solar particle event. And finally, as mentioned in the title already, I think it can have impact to nuclear and particle physics. So TIMEPICS-3 detectors were recently installed in Atlas, where they are used for particle tracking and the radiation field characterization. I will show a few slides on this in the following. And I also think it would be good, especially in nuclear physics, for example, for some measurements where you want to reconstruct vertices or do angular correlation measurements. And also during when I prepared for this talk, I found a paper which discussed the potential of hybrid pixel detectors for the search of neutrino-less double beta decay in cadmium-116. And the idea there is to use this kind of pixel or this 3D information to separate single beta decay from a double beta decay. Okay, so just as promised, few slides on Atlas, so it's very short. So in 2018 and 2017, we installed in total 4 TIMEPICS-3 detectors to the Atlas cavern. The locations are shown here. This is the first one, this is the second one. The other locations are from the predecessor network, this TIMEPICS network. And we wanted to study how or if they can be used for luminosity measurement. With the time resolution of 1.56 nanoseconds, we should also be able to do it finally bunch by bunch. And to do radiation field characterization, which is then used for benchmarking the Atlas simulation. And moreover, we found out that we can nicely measure induced radioactivity at the positions in the Atlas cavern. And our plan for the Run 3 upgrade is to install 14 TIMEPICS-3 two-layer stacks. Here I will just outline very few results related to particle tracking and the measurement of MIP, minimum ionizing particle fluxes. So first thing you see here is that this is just the unfiltered data set for 10 seconds integration time of the detectors which are at the extended barrel. And now from these data, we try to select kind of straight tracks. And if you do this—
2 minutes, Benedict. Yeah.
Sorry, I have how much? 1 minute, 2
2
minutes?
minutes.
2 minutes, okay,
yeah.
I will manage this last slide, okay. And then you can reduce it to this smaller set. And from this set, we then calculate the stopping power spectra. We had 2 detectors in this position, so you can see here 2 lines. And these stopping power spectra, they nicely correspond to stopping powers of minimum ionizing particles. And also using the tracking or the angle reconstruction, we can create a map of the directionalities of these minimum ionizing particles. And what we see is that most of them come from here, and this aligns actually with the interaction point. And then I will just conclude. I have shown that TIMEPICS-3 allows a 3D reconstruction of particle tracks. I have discussed the methodology, and I have shown that in 2 millimeter thick cadmium telluride detector, it's possible to achieve 60 micrometer precision, whereas in a 500 micrometer thick silicon sensor, we can get precisions or resolutions in the order of 30 micrometers. And I have shown only 1 experiment profiting from this TIMEPICS-3 capabilities. But if we go to additional slides, I put there a second experiment, which is more on the edge of nuclear physics and particle physics. And with this, I thank you very much for your attention.
Super, thank you very much. Do we have any questions for Benedict?
Yes, hello, this is Karol Czerny. Maybe I would have a question, if I may.
Yeah.
You said the time resolution is around 1 nanosecond, but okay, that somehow corresponds to the time resolution of the whole sensor, right? The time because you reconstruct the tracks from the time differences between the pixels, and this must be much better, no?
Yes, so the time resolution I give there of 1.56, it's maybe it's related to the clock frequency which is used to sample the TOA. So we have a 640 megahertz clock which samples the timestamps. So this is this 1.56 nanoseconds. And then what contributes to the resolution, for example, in cadmium telluride, you have some local variations of drift times due to effects of the crystal. So of course, this is why I had only 60 micrometer precision for cadmium telluride, because I do it globally for the whole matrix. So probably if you would look locally, you could even improve it a bit. And I'm not sure if I answered this correctly. If you consider, if you want to measure, for example, gamma ray flashes, then of course the drift time is the limiting factor for resolving these pulses. So if I would have to say I should give a number of the time resolution of time peaks, let's say with 500 micrometer thick silicon sensor for measuring gamma ray pulses, I would say it's actually worse than this 1.5 nanoseconds, because you have to consider the drift time differences.
Okay, I think about it. Thank you.
Okay.
Thank you. One last question for Benedict.
Maybe I would like to ask, you need very probably need to study the distribution of the electrostatic field in your sensors. How are you doing this? You are using some TCT or transition currents or something like this, some lasers?
To be honest, it's possible to measure the electric field with lasers, yeah. But what we did, we just used like the tracks for calibration. So if you have particle track going through, you can estimate where it started and where it ends from the pixels actually. So you can measure then by looking at the drift times how it should look like, and then I compare this to my model, and then I can see if it fits or if it doesn't fit. In fact, it would be excellent to have an independent measurement of the electric field, but for these precisions, it was not necessary, to be honest.
Okay, thank you.
Okay, thank you. Benedict, quickly, in your Atlas measurement, you already had a 2-layer stack sensors installed in run 2, or this is something new for run 3?
In fact, we had 2 layers installed, but they were not aligned properly. So we just put 2 layers which were synchronized, but they were not aligned. You would see tracks going from one layer to the second layer. They were only in similar positions because there was some space. We didn't have enough space to put them directly behind each other, so we put them more like next to each other.
Okay, I understand. Okay. Thanks very much. I think we can have more discussions on this topic in the Mattermost. I think there are probably more questions. Thank you very much, Benedict.
Okay, thank you very much.
Okay, so I'm pleased to introduce our next speaker. So Luca Nizzoni from University of INFN and Ferrara. And we'll switch now to LHCb. And Luca will present the upgrade of the LHCb rich detector. Luca.
Yes, can I share the slides?
Sure, yeah, go ahead. Thank you.
Okay, tell me if you see the full screen mode.
Perfect.
Okay, so just a second. Okay, good morning, everyone. I am Luca Menzoni from the University of Ferrara, and today we'll talk about the LHCb rich upgrade. At slide 2, okay, since many other persons have already talked about LHCb, let me skip the general introduction. Let me just say that in this talk, I will focus on the 2-ring imaging Cherenkov detectors of the experiment, Rich 1 and Rich 2. Now, at slide 3, Rich 1 is designed to detect particles up to 60 GeV/c, and its angular acceptance is the full LHCb1. Rich 2 has an angular acceptance of 15120 millirad and covers the high momentum region up to 100 GeV/c. Both Rich detectors use a gaseous Cherenkov radiator, C4F10 for Rich 1 and CF4 for Rich 2. The Cherenkov rings generated in the gas are reflected from a spherical mirror to a flat mirror onto the photon detector plane. The photons are detected using hybrid photon detectors with electronics of readout working at 1 MHz embedded in them. On the right-hand side plot, you can see the excellent rich particle identification performance on the kaon identification and the pion misidentification efficiency as a function of the particle momentum. For more efficiency plot, I redirect you to the Martina Pili's talk. Now, at slide 4. From the end of last year, the LHCb experiment is undergoing a major upgrade, which is enabling it to acquire data at 40 MHz and to operate at increased luminosity of 2 × 10 to the 33 centimeters to the -2 seconds to the -1. And following this increase in luminosity, The RICH1 detector is having its optical system redesigned, while the HPDs and their 1 MHz limited electronics are being replaced by commercial 64 channels multi-anode photomultiplier tubes read out by the Claro ASIC. The data acquisition will be performed using FPGA-based digital boards transmitting data via gigabit transceiver chip. At slide 5, we have the key condition for the RICH detectors, which have to have a peak occupancy under 30% on the photon detector plane. To satisfy this condition with increased LHB luminosity, the RICH1 spherical mirror and the focal plane are being moved downstream with respect to the original position to increase the ring size. Having a longer distance to travel inside the RICH1 gas enclosure, the particles will generate more Cherenkov photons with respect to the actual conditions. Both a new spherical mirror with increased radius of curvature and a larger gas enclosure are needed. Given the little space remaining for the readout electronics, a compact system front-end readout is required. At slide 6, the MAPNTs used in the LHCb RICH upgrade are produced by Yamamatsu Photonics. Two types of MAPNTs are used in the upgrade, the R13742 model with side of 1 inch and the R13743 with side of 2 inches. For the upgrade, a total of 3,100 1-inch PMTs and 452 inches PMTs are needed, spares included. They are equipped with the UV glass window and ultra B-alkali photocathode with a peaked quantum efficiency on the blue wavelength spectrum, resulting in a reduction in the chromatic error. The minimum guarantee gain is 10 to the 6th with a bias voltage of 1 kilovolt, and the maximum pixel-to-pixel gain spread is guaranteed between a pixel of the same PMT. A constraint on the maximum dark count rate is also applied. Slide 7. The electronics complex system is called elementary cell, and it is the fundamental block of the LHCb RICH upgrade. In the elementary cell, the PMTs and the readout electronics are grouped together. Two different types of elementary cells are installed in the upgraded RICH detectors, R-type and H-type, depending on the MAPNT model used, which have been validated with a dedicated quality assurance procedure. The H-type elementary cell, used only in the lowest occupancy region of RICH2, has a single 2 inches MAPNT, while the R-type elementary cell, used in RICH1 and in the highest occupancy region of RICH2, has a 2x2 array of 1 inch MAPNTs. These MAPNTs are housed in custom sockets on the so-called baseboard and are read out by the Claro ASIC, soldered on the front-end boards. Data are acquired by an FPGA-based digital board, and fabs and digital board are interfaced via the backboard. The elementary cells will be grouped in photon detector modules, PDMs, columns of 4 elementary cells read out by 2 digital boards each. Slide 8. The Claro ASIC is an 8-channel amplifier discriminator designed in 0.35 micrometers IMS CMOS technology for single photon counting coupled with MAPNTs. To operate at 40 MHz, its recovery time is less than 25 nanoseconds, and the low power consumption per channel avoids the need for additional cooling on the front-end electronics. Each channel is equipped with an adjustable threshold to compensate for channel-to-channel gain variation on MAPNTs. The ASIC radiation hardness has been intensively tested on some of the most advanced European irradiation facilities. To prevent register misconfiguration triggered by the incoming radiation, the Claro is equipped with triple modular redundancy protection system. Slide 9. A prototype of the LHCb RICH upgrade detector has been tested in a realistic environment at the beam area of CERN using charged hadrons. One PDM with H-type elementary cells and one PDM with R-type elementary cells have been used, read out by digital boards. A borosilicate plano-convex lens has been used as a Cherenkov radiator, and the Cherenkov photons produced inside the lens are directed onto the MAPNTs using an internal reflection system. A live monitoring software allows the user to see Cherenkov rings in real time, as you can see in the right-hand side picture, where the Cherenkov rings seen on the software have been projected on the PDMs for display purpose. A light-tight polypropylene box has been used to ensure total darkness and thermal insulation, and humidity is controlled with nitrogen flow in the box. In the test beam, the elementary cells have been characterized and data have been successfully acquired using the optoelectronic chain, which is used in the REACH upgrade. So slide 10. The excellent LHCb REACH time resolution is mainly due to the prompt Cherenkov radiation and the focusing geometry of the detectors. The signal from a single proton-proton interaction fits within a window of approximately half nanoseconds at full width of maximum. The left-hand side picture shows the simulation in the LHCb framework of the time of arrival of photons at the REACH1 photon detector plane with an LHC batch crossing time at 0. A time gate of few nanoseconds can be applied to the signal peak, which is named S, to collect all the signal while rejecting out-of-time background. And in addition to the LHC background, the time gate also reduces MAPNT's dark counts and out-of-time after pulses. This was studied during the beam test on the REACH upgrade prototype, and the results can be seen in the right-hand side picture, where the signal-to-noise ratio improves using a 6.25 nanoseconds time gate. Slide 11. Dedicated quality assurance tests have been developed to validate all the components of the LHCb REACH upgrade, from the MAPNTs to the support components. But since this was part of my PhD, let me present to you the Claro and the elementary cell quality assurance procedures. For the Claro quality assurance, a pick-and-place automatic attestation has been developed to validate the ASICs, ensuring the proper functioning and measuring their main parameters. The test station is controlled via PC, and the control software has been developed in National Instrument LabVIEW. After passing the quality assurance test, the ASICs have been soldered to the FEBs, which have been then validated using a digital board-based test station controlled via Python scripts on a PC. Slide 12. The ACQA test station is a dark box equipped with air cooling system and temperature and humidity live monitoring. Up to 4 elementary cells can be tested simultaneously in a box, read out by digital boards. An LED driver is used to illuminate the MAPNTs in a controlled way to perform characterization tests on the Claro coupled with the MAPNTs. During the test on the elementary cell, the Claro main parameters are measured again, and a comparison with the results from the Claro QA test is performed to ensure the soldering procedure didn't affect the ASIC performance. The station is PC controlled, and the control software is an automatic finite state machine that has been developed in LabVIEW. The elementary cells passing the quality assurance test have been sent to CERN to be mounted in the upgraded REACH detectors. And this CQA has been a challenging task for the great number of channels to be analyzed at the same time. When 4 elementary cells of the R-type are tested, it means that 1,024 Claro channels have to be analyzed at the same time. Slide 13. The REACH2 detector commissioning is progressing rapidly, despite the delay introduced by the COVID-19 situation. The elementary cells have been assembled in PDMs, then in columns to form the PD planes of the new REACH2. At the same time, the services, the mechanics, and the readout of the new detector have been assembled. And I also have the pleasure to inform you that 1 week ago, on the 23rd of July, a test installation has been performed on the A side of the upgraded REACH2 detectors of LHCb, which means we're almost ready to switch on. Let me also talk about the foreseen performances of the upgraded REACH detectors. On the table you find in this slide are reported the Cherenkov error contributions for the actual REACH detectors and the expected one from simulations for the upgraded REACH detectors.
Both 2 minutes.
Yes, thank you.
2 minutes, yeah.
Thank you. Both REACH1 and REACH2 will have a lower Cherenkov error thanks to the upgrade operations. On the right-hand side of the slide, you can see the REACH Pion miss ID versus the Keon ID plot for 3 different running conditions. The black line refers to the actual REACH detectors at the run 2 luminosity. The red line represents what we would like to operate the actual REACHs at the post-upgrade LHCb luminosity. That's why an upgrade is needed. And lastly, the green line is the expected performance with upgraded REACH detectors in the post-upgrade luminosity conditions. And let me just conclude that after the upgrade, the LHCb luminosity will increase by a factor of 5, and the readout frequency will be of 40 MHz. To be able to efficiently acquire data, the optical system of REACH1 needs to be modified to decrease the occupancy on the new photon detectors which are DMAking, these multi-anode photomultiplier tubes, which are installed in the elementary cells and read out by the Claro ASIC. All the ICHEP grade components have been tested in BIM experiments and the laboratory setups, while dedicated quality assurance procedures have been developed to validate all the components to be installed during the upgrade. And almost all the elementary cells have been delivered at CERN for commissioning, and RICH2 commissioning is almost complete. We are very ready to install in the cavern. Thanks.
Thanks very much, Luca.
Thank you all for listening, for the chance of giving this talk.
Thank you. Are there questions for Luca? Clearly a huge amount of work, and congratulations on the installation of the side A.
Thank you very much.
That's great. I have actually a very naive question on your slide earlier in the talk where you show just a schematic of the, I think slide 5. I didn't quite understand the slide 5.
Yeah, sorry.
Yeah, no problem. I didn't understand the mirrors and how you will monitor the efficiency of these mirrors with radiation damage.
They have been tested. Now, I didn't prepare a backup slide, but the material has been tested for not quite, not only radiation damage, but also, let's say, radiation transparency. This is what worries the most. But this material, which is glass, I can send you the details if you want later on, has been proven to be radiation harder and also radiation transparency. So they don't contribute to the material budget to be accounted for when talking about secondary radiation caused by particles colliding with the LHCb material, let's say.
Okay, super. Yeah, if you can post on the Mattermost, that would be great.
Yes, for sure.
I'd be curious, yeah. Other questions for Luca? Okay, thank you for this very detailed talk and congratulations again and also for your PhD work.
Thank you very much.
That's super. Yeah. Okay, and go to our next speaker. Okay, so we pause for a second from LHC and we go to Bell, and Oscar Hartwig will present the time of propagation barrel particle ID detector in the Bell 2 experiment in Japan. And Oscar's from the University of Hawaii, and it's evening for him. So we thank him for joining. Yeah. Please go ahead, Oscar.
Thank you very much. I hope you can hear me well. I hope you can see the slides well. So this is about the barrel PID system of the Bell 2 experiment. So here on slide 2, we have the cross sections of the old Bell 1 experiment on the lower half and the cross section of the Bell 2 experiment in the upper half. And you see, at first look, not much has changed. It's still the same geometry. It's still the same mechanical structure. But if you look into the rough details, then you will see that, for example, this yellow part, our drift chamber, our main tracking chamber, is actually larger than it was before. And for that reason, there's much less space, especially in the barrel region, for our dedicated Cherenkov-based pion-kaon or particle identification systems. So something entirely new had to be done. In addition to this, with the expected beam backgrounds, whatever was used previously would not have worked at all. So we needed something entirely new, entirely from scratch. And this is what was developed for this and is now installed and fully operational. And that is our time of propagation detector, the top detector. The working principle is fairly straightforward, or maybe not. Of course, we use Cherenkov information to reconstruct our particle species. And we do this with a fairly highly refractive radiator medium, which is a quartz in our case. So when a charged particle goes through the quartz, as you can see here in this small diagram at the bottom, some or most of the Cherenkov photons can actually be captured inside the quartz and be captured by total internal reflection. And in that case, the angular information of these Cherenkov photons is actually conserved. If all of the surfaces are smooth, finely polished and square with respect to each other, right? Because then the photons will bounce around, but they will never lose their angular information, which carries the actual information on the particle species. Now, we don't have the space, and also it wouldn't work from a background radiation perspective to actually project out these rings so that we get actual rings again. Instead, what we do is we measure the time of propagation of individual Cherenkov photons. So you will also see this here in this diagram again. Say the red line here is a hypothetical photon path of a Cherenkov photon generated by a pion, and the blue one is the one that would be generated by a kaon. See, the pion has a slightly larger opening angle because the pion is a little bit lighter than the kaon. And thus it has less bounces until it reaches one end of the bar, where we can, for example, read this out. And thus, if it has less bounces, it has a shorter path length, and thus a faster propagation time towards one end of the bar where we can read out these photons. So on average, of course, this is very complicated in practice, but on average, earlier arrival time of a photon means it's a higher chance that this was a lighter particle, thus a pion over a kaon, for example. At the same time, we are at a collider machine. We know our collision times very well. We implicitly, when measuring these arrival times of these individual photons, we fold in the time of flight of the track from the creation all the way until it hits our quartz bar. So we always do an integrated time of flight measurement at the same time. If we would just do time of flight or time of propagation measurements of these photons, we wouldn't really get very far, because chromatic dispersion is really the fundamental limit of such a time of propagation device. I will get to this in one or two more points where this is limiting us. Similar approaches are currently being done by the LHCb Torch project. Also, the Panda Dirk is using this, but I think we are the first people to actually build a device like this and operate it. So in our specific case, we have 16 of these quartz Cherenkov radiator bars arranged around the IP, as you would expect for a sort of barrel geometry. They are about 2.5 meters long. One end, the forward-facing end, has a mirror that reflects backwards facing photons back to the front. The mirror actually has a sphericity to it, so it focuses backwards facing photons onto individual points, which helps with a chromatic dispersion. And at the same time, it also projects out the thickness of the bar for photons that go backwards. It only helps you for the half of the photons that go backwards, but it helps nevertheless. And then on the backward side, we have a small expansion prism to expand these ring images at least a little bit. And then we have these sensor bars here where we collect photons and measure them with very fast timing. So to realize a project like this, you can go through these exercises and see what you need in terms of resolution numbers. And it turns out the goal is better than 100 picosecond time resolution on single optical photons. For this, you need a sensor that can do this. So of course, it needs to be efficient for single photons, needs to be better than, say, 50 picosecond single photon timing resolution. You want a few millimeters of spatial resolution. You need to be able to operate in a B field. We are inside our solenoid. So all that is clear. And then, of course, you also need some electronics to read all that out at the fairly high luminosities and thus fairly high trigger rates and beam background occupancies that we expect at Bell 2 eventually. So for sensors, we use microchannel plate PMTs. They were developed more or less specifically for our project in a joint venture of Hamamatsu and Nagoya University. They spent many, many years developing these things and ultimately came up with something where the single photon timing resolution is better than 40 picosecond on a test bench. So it's exactly what we're looking for. They are mostly resistant to B fields. You need to adjust the bias voltage a little bit, but it works well. They have pixelated anodes of roughly 5 by 5 millimeters squared. So we also get some geometric information. That is great, but they have a fundamental drawback. The fundamental drawback is they do have a sort of lifetime. So they can only see a given amount of integrated charge. They amplify a given number of photoelectrons before they go blind effectively. And during this whole R&D to get this project going, they first managed to converge on what we now call the conventional type, where sadly the lifetime or the integrated charge before they would start to lose efficiency was only about 1 coulomb per square centimeter. They had to start producing these at some point to have sensors at all for the project. So roughly 50% of the current top system is instrumented with this conventional type microchannel plate PMTs. But of course, they continued their R&D efforts during the production, and then at some point had this breakthrough where they managed to build these life extended types that are using atomic layer deposition to extend the lifetime of these. And then you get more than a order of magnitude more in lifetime. So you get more than 10 coulomb per square centimeter. So 10 times higher lifetime. And they switched production to this type in the middle. So the other half of the currently installed top system is already equipped with these life extended atomic layer deposition PMTs. So how much charge do you see on such a PMT over the lifetime of the experiment? Well, this is entirely dominated by the beam-induced backgrounds. Just the luminosity itself, the physics events themselves, they are a minor contribution to the whole thing. So it's just sort of beam backgrounds, and the beam backgrounds can be divided into the irreducible components, which is scales with the luminosity. It's just luminosity backgrounds. Which will be up to 7 megahertz per PMT at the full luminosity, has an angular dependence, which you can get from Monte Carlo, but this is kind of the range that you're looking at. So this is quite large, obviously, but this will only happen at this full scale at full luminosity of the Super KEK-B machine. The other beam backgrounds largely depend on the accelerator conditions and how well the collimation is tuned, etc. So you have some jiggle room in this, right? You can ask the machine people to please tune the beams a little bit better to maybe reduce this, or you can also set limits and say we don't want to run higher than this. So in the bottom right here, this is the projection of the luminosity over the lifetime of Super KEK-B and BEL2, so over the next roughly 10 years, and you will see that the expectation is that the instantaneous luminosity is more or less continually increasing over time, and this you can then translate into how much charge do we expect to see on our PMTs. Which is shown here, which for some assumptions say we can keep these other beam backgrounds below 1.2 megahertz per PMT, that by over the next 10 years, we will integrate something like 6 coulomb per square centimeters on average over the various PMTs, which will just fit into the budget of say 10 coulomb per square centimeter. That these PMTs will be able to do. So if we can reach this and if we can keep within this, then these PMTs will be good enough, at least the 50% that are life extended already. But this critically depends on the fact that we can keep to this, say, 1.2 megahertz per PMT of reducible background, so that the machine will be tame enough and low background enough to keep to these numbers. So going from this, you can then see how will your quantum efficiency, your PID efficiency actually evolve over time. And you will see here, so this is the curve for the conventional PMTs, where half of them are currently conventional PMTs. And you see within the next 1 to 2 years, they will start to degrade. And if we would not replace them in 2022, they would basically go down to 0 very, very quickly, and half of top would be useless. We do have a time window in 2022 because there will be a long shutdown anyway, or a longer shutdown anyway, to replace all of these PMTs, so that all of the current conventional PMTs will be replaced with these life extended ones. And then we hope that with these life extended PMTs, we can go all the way to the end of the experiment. Production for these new PMTs and testing is well underway, of course. We will see how COVID will influence this, but we think we are on a good track. Okay, in terms of front-end electronics, we do have 8,000 channels of effectively 3 gigasample per second oscilloscopes on the chips. This is on a chip. This is a custom ASIC developed here at the University of Hawaii. We have shown the electronics time resolution is better than 50 picoseconds. Of course, you do full waveform extraction. That means you get a lot of samples. You cannot transfer them out. You need to do full feature extraction inside the front ends. Only transfer out the photon timings. Everything else is impossible, but we have very powerful processing in the front end. We have more than 300 FPGAs right in the front end, 640 ARM cores. We have plenty of resources available still where we can put more stuff into this to refine our online processing. So it just needs some smart ideas and some implementation to put more and more things into the front end. Eventually, maybe power budget might be a problem, but it's a very interesting thing to do and to work on this. If you're interested in this, there's a link to a whole paper that describes this front-end electronic system. Just for some performance numbers, we managed to get the intrinsic time resolution for most channels, 99% of channels or so, to below than 100 picoseconds.
2 minutes, Oscar.
Yeah, okay. We're dominated by some electronic noise in the signal chain because we operate the PMTs at fairly low gain. Fine. Recently, we managed to implement or improve our time walk correction by quite a bit. So now most of the channels are, even across the whole amplitude spectrum, are better than 100 picoseconds. This is great. Effect on the PID performance is very low because we're limited by chromatic dispersion in the end. this is how this actually looks like. This is just a kinematically tagged kaon, and this is the black points are the measured photons we get from this. So it's like 20 or so. You can compare this to different PDFs that are shown in the background here. You can see the kaon one fits best by eye, but also if you do the likelihood, if you compare data in Monte Carlo, we're getting closer and closer. The data is getting closer and closer to Monte Carlo, but we are not just there yet. It's a new system. We need to gain a little bit more experience with it. So quick word on what we still can improve and what we are working on. The reconstruction of top entirely depends on how you generate these PDFs that are shown here in the background. We do have a very fancy way of generating this analytically as a function of the track parameters, but we know it's not perfect. There are continuous improvements on this. Now we have an analytic treatment of delta rays in there, which is really cool. You can again read this paper here for more of the details. It's really fancy. You can do some very detailed studies, which yields beautiful plots, as I show here on the right side. But of course, we also try to use modern machine learning techniques. So there is a whole task force of PNNL, University of Hawaii, KIT Nagoya, INFN Torino that work on this, both for simulation of top events as well as reconstruction. So we are trying to make use of this as well. The beauty of all of these studies is they have the potential to not only improve data Monte Carlo matching, but also the top performance by itself, right? So even the performance of top in both data and Monte Carlo might improve considerably from these studies. So this is quite cool.
You must wrap up, yeah, Oscar?
Yeah, to summarize, top detector is a rather novel system, I think. I think it's the first time that this time of propagation principle has been installed. We have quite strong requirements on sensors, etc., but we managed to reach them all so far. Top performance is getting very close to Monte Carlo expectations, will clearly improve in the future. Many Bell2 analyses that are shown first time at ICHEP here are using the top PID, so it is everybody uses it, and we need to replace half of our PMTs in 2022, but we are going to do this because there is some time for this anyway.
Thanks very much. Super talk. Very, very clever detector. Are there any questions for Oscar?
Thomas speaking. I have a question to the slide 11. I raised hand just in case. On the scale, it's a time resolution and not in nanoseconds, but in picoseconds, I think you mentioned, right? In the left plot.
On the left plot, this is the y-axis is nanoseconds.
It's nanoseconds, but you mentioned pico.
Yeah, it's 0.1 nanoseconds, right?
Okay,
so it's 100 picoseconds.
So 100 picoseconds. Okay.
Yes, yes. 100 picoseconds.
Yeah. So when you talk about the single photon time resolution, how can you go with a very low gain? What does it mean? I mean, what is a gain? That's my question.
The gain is the gain of the PMT tube itself. How many electrons you?
That's fine,
the electron
how much? I mean, it's 700, 1,000, 10,000.
Currently we run at 30,000. 3 times 10 to the 5, I believe.
3 times 10 to
yeah, here
4.
Roughly they are scattered a little bit around this, but we run at 3 10 to the 5. Yes.
3 10 to 5. Okay, thank you. And last question. I mean, because sorry, I did not catch it. I mean, a rate. You do not observe any problem with a rate. I mean, that you go to the saturation regime with your MCP PMTs. That's
not never. We never expect this from physics or beam backgrounds. So they could do very high rates. One recent problem that we have seen is that some PMTs become hot, or individual channels of PMTs become hot and start to fire, most likely by themselves. And then they start to basically self-saturate. But this is not a fundamental problem. This is most likely a thermal problem on individual channels or something like this.
Okay, I don't quite understand, but it sounds interesting. But I will stop here. Thank you very much.
Thanks very much. Thanks for your questions, Tom. I think this talk deserves some more discussion in the Mattermost channel.
Yeah, I finally managed to log in, so I'm there, and I will try to answer more questions if there are more questions.
Okay, perfect. The link to the Mattermost channel was in the chat earlier, the video chat. If anybody needs it, we can post it again. Okay, thanks very much. So now we switch from Bell back to the LHC, and we're going to focus on forward detectors. for the next three talks. And I'm pleased to introduce Jessie Liu from the University of Chicago. And Jessie will present the alignment of the ATLAS forward proton detector. Would you like to share your do a sound check?
Yeah, hello.
Hello, hi.
Okay,
Super.
so hi everyone. So I'm going to be talking about the forward proton detectors at ATLAS. So this is on behalf of several people's work. And for me, I think what's so interesting is that it's not every day we install and we commission a new class of instrument at the LHC. And today I'm going to focus on the detector performance side of things. Some of the physics will be discussed actually in sessions after my talk in a different track. So I'll focus mainly on the technical aspects, so an overview of the reconstruction and the detector, and focusing on the alignment methods. And I'll briefly touch on the efficiencies at the end. So I want to flash up this event display from a 7T EV run, which is one of the key targets that we look for in these in this detector, which is photon fusion production of 2 leptons, right, turning light into matter. And if you didn't have the AFP, these forward proton detectors, you could only see these central 2 leptons here, right? So this is a dielectron event. But with the AFP, we can actually see these forward protons that are going down the beam pipe here. So slide 4, you can see this Feynman diagram. I've zoomed into this interaction here of these 2 leptons produced via photon fusion. And in these processes, the proton can stay intact, right, because of an electromagnetic interaction. And so they travel along the beam pipe and they are deflected by the LHC magnets, and you can insert these silicon trackers down to a few millimeters from the beam pipe, which is a bit like what LHCb does, to detect these scattered protons. And the key observable that we measure in this detector is this fractional energy loss of the proton, this psi here, which I define here. So these detectors are placed just over 200 meters downstream from the interaction point. So that was the cartoon. Here's the more technical diagram with all the different quadrupole and dipole magnets, as well as the collimators. And you can see the AFP sits downstream here. They're installed either side of ATLAS. You can see I've marked the directions towards LHCb and ELISE. And each side has 2 sets of stations, a near and a far station. And each station has 4 planes of silicon. And the far station actually has these time of flight bars that will actually be discussed by Karel in the next talk. And so the one of the arms was installed in 2016, and in 2017 we took high luminosity data with both arms installed. So slide 6 is just a photograph of one of these far stations where you can see the nice silicon. These are edgeless pixel sensors, 3D pixels, which are very similar technology to the innermost pixel layer that we have in ATLAS. And you can see these scintillating time of flight bars on the left. So slide 7, just to give you a sense of what is a proton spectrometer, right? So a spectrometer is a device that converts spatial measurements into energy measurements, right? So because the protons, they lose a bit of their energy, the Lorentz force from the LHC dipoles actually bend them slightly less than they otherwise would. And so they get deflected and are displaced by this X position. And from this position, if you calibrated your spectrometer, you can infer how much energy the protons have lost. And so that's what this psi parameter is. And this is very interesting because you can then infer how much energy is emitted by the proton into these colliding photons. Right? So you have complete determination of the photon-photon system independent of the central detector, which can be very interesting for dark matter searches, for example. So one of the first things I just want to show a slide on is the interplane alignment, right? So on the top left, you can see a picture of ideal alignment of the 4 planes, right? When a proton goes through, the distance that the proton, the hits and the clusters that they leave relative to the detector edge is the same in each plane. But in reality, there may be some imperfections, and actually you measure different distances with respect to the detector edge. And so this, we apply an iterative comparison between the clusters and the tracks and minimizing their chi-squares. And we can actually align these clusters with respect to the track. So that's what you can see here in one of the planes in the A near station. The red is after this alignment procedure. You can see more details in this link down here. Now, slide 9, I want to focus a bit of time onto something which actually has a bigger impact on our physics analysis, which is the global alignment. Right? So the idea of global alignment is that, as you can see here, we're converting a spatial measurement on the vertical axis to this energy momentum measurement on the horizontal axis. And these red markers are the simulation of the LHC optics as the protons are transported through the beam pipe. This is done with the MADX software package, which for accelerator physicists is their standard software simulation package. And you can start to get a sense that if you don't know the zero offset, right, this absolute distance between the detector edge and the beam, this parameterized line here, right, the simulation, will move up and down because that's the zero offset. And that will have a direct impact on the left to right of what you infer as the measured energy. Right? So this is why we need to calibrate this absolute offset, which is essentially an absolute scale on the proton. So one of the most canonical ways to determine what is the absolute position of the beam relative to the detector is beam-based alignment. So this is getting into sort of more technical details related to accelerator physics, right? This is a journal article about this method with a very nice picture from an accelerator journal. So just to give you a simplified picture, as many of us are more detector physicists, the main idea is to insert these collimators, which usually protect the LHC, the expensive magnets, for example, from stray particles from the beam. You can insert these collimators into the beam to probe where the beam is, and as soon as it touches and probes the beam, showers will be induced. And you can detect these in these beam loss monitors, right? These BLMs, which are placed at regular intervals along the beam pipe. So it's a fairly intuitive idea, really. You're just probing where the beam is and detecting the showers from the beam. So this is a screenshot from one of these dedicated runs back in 2017 when these detectors were first installed. And on this lower panel, you can see is this position of these collimators. And unfortunately, the scale is a bit too large to see the variation, but the collimators are changing position. And on the upper plot, you see this spike, which are the showers from when the collimator touches the beam. So this is a way of determining the absolute position of the beam relative to the detectors. Now, one of the methods that we are developing inside Atlas is a novel in situ calibration technique. Right? So this is going back to our dilepton signal, and we're using this as a standard candle, which is what we might call a J-psi of the AFP. So here's the diagram again. So what we want to do is we want to tag these 2 leptons that we produce. And on this right-hand side, you can see I've placed a formula, which is very similar to the Bjorken X formula, where if you know the dilepton mass and its rapidity, you can calculate by energy and momentum conservation the expected energy loss of a proton, right, this psi LL. And then you can do the inversion of the spectrometry relation, and you can determine the expected position in the X. And then you can probe the proton this X AFP and see if they are the same. And for the signal, so these are these black points here where the protons arrive from the same vertex as the dileptons, there will be a kinematic correlation. And for the background events here, this is from mixing the data events, the red points here, you can see these are when the protons arrive from pileup, from a different vertex. They have no correlation. Now on the right, you can see this background subtracted version of the left, so the residuals, and you can see that there's a slight offset, right? So the beam-based alignment techniques were not completely determining the absolute position of the beam. There was some systematic shift. So then you can imagine a fairly simple way to correct for this, which is just an additive correction, shifting this peak back to 0, right? So you're just fitting and shifting the residuals. So
Jesse, 2 minutes.
Thanks. So this is what we've done, and this is only possible because we have enough luminosity to see this dilepton signal peak. Now, just to give you a sense, a slide on the systematic uncertainties, this is a pretty robust method, right? Because as soon as you've seen this peak, there's not really any other way you can constrain this peak. And so you can change all the different cuts, the analysis cuts that you use to select the peak, and the peak actually remains fairly robustly centered around 0. And for now, we're assigning quite a conservative 300 micron systematic, but you can see that this is somewhat conservative, and there's a lot of room for improvement. So just to flash up some of the other important ingredients for the physics analysis, which is the data quality and efficiency. So this is an estimate of the efficiency of each station using a novel station-based tag and probe technique, where you use the near station to tag a track and see what fraction of events have a matching track within 2 millimeters of X reconstructed in the other station. And so you can see that the near stations have a slightly lower efficiency than the far stations, just purely because of showering effects, right? This is about a 4% effect that we're quantifying here. So I just want to end with this cartoon that many of us might be familiar with of what we can reconstruct inside the Atlas detector, right? There aren't actually many objects we use inside Atlas. And what is so exciting about these forward proton detectors is that we are really expanding our repertoire of what kind of objects we can reconstruct at the LHC, right? This is a genuinely new kind of object that we're probing for the first time. So my last slide, just to summarize, we are developing a lot of innovative and pioneering strategies to align the AFP detector and characterize its performance, which is critical for opening this new kind of program at Atlas. And you can see there's going to be a wealth of talks, one straight after me, as well as in other tracks today, discussing the new physics results that we're exploiting with all this. So thank you.
Super, thanks very much. Yeah, clearly very challenging experiment. Lots of interface with the LHC as well. Any questions for Jesse? Patrick? Yeah.
Hi, hello. On slide 8, please, when you talk about the local alignment. So do I understand that you are using track-based alignment, right?
Yes, that's right. We're comparing the cluster positions to the track reconstructed.
Yeah. And then you said
minimizing the residuals.
You use an iterative approach, right?
Yes.
Did you consider using a global approach when you fit both track and alignment parameters in a single fit? That is usually less biased.
I'm not sure. I think.
Okay, and then
follow up.
Yeah, and then I have another question. Do you observe weak modes, so invariant non-physical distortions? I mean, sorry, non-physical distortion, systematic non-physical distortions.
I think right now we're not seeing any evidence of that.
Okay.
I think we only correct the X, Y, and the rotation about the Z position. So I don't know if we're sensitive to those weak modes.
Yeah, of course, because your system is symmetric. Yeah, I mean, if you, for instance, move all your your modules consistently, you make a global transformation, for instance, along Z, then your tracks will still look good. They will still look good in terms of chi-square. So you might be sensitive to weak modes. You might want to check that.
That's a good suggestion. Thanks.
May I have a question to your question, please? I mean, by this physical distortion, what do you have in mind, please?
Yeah, as I said, for instance, if you make a global transformation of all the modules along Z, so that can affect resolution. Sometimes these weak modes, in the end, they don't really affect the physics, but they can. So one needs to be careful about them. I mean, you don't want to introduce a non-physical transformation in your alignment.
My question was rather about what is the causing of this, what you have in mind, but I will stop here and we can discuss on Mattermost, for example.
Okay. Yeah.
Thank you.
Yeah.
Okay, so other questions for Jesse? Okay, let's move to the next talk, which is still on from Atlas. Okay, and here again we have a Czech local. Yeah.
Yes.
Okay. Okay.
So hello. Can you see the slides in the presentation mode now?
We don't see full screen. If you can go to full screen, Carol.
Okay. View presentation should be working now. Is it? No.
I don't see full screen, but
I'm sorry. I will do it once more. Sorry.
No
Okay.
problem.
Share this one. Okay, otherwise we will have to stay with this presentation.
Okay.
So
I think it's okay. Yeah,
it's okay.
We
Is
can
it okay?
do, we
Okay. Okay.
We can
sorry.
work like this. No,
yeah,
no problem
sorry.
at all.
I
Thank
don't know
you,
what
Carol.
happened. Yeah, I don't know what happened when I tested it before. Okay.
It's
Hello.
no problem.
Hello. I would like to thank the organizer for giving me the opportunity to present the study of performance of our time-of-flight detector, which is a part of the AFP detector. I could not wish to have a better introduction to AFP than it was given in Jesse's talk, and also in some sense it's nice that we share the same concerns in our detectors, which were also presented in Oscar's talk. I have in mind mainly the problems with PMTs and so on. So I would like to present the performance study that was done with the time-of-flight detector in the Atlas data that were acquired in the year 2017. I will probably go directly to what we have. The proton tagging was already well described by Jesse. What we have is the situation that we have reactions where there is a colorless exchange. It can be a partoning colorless exchange, a diffractive one, which we call usually a pomeron. That can be realized by a collective state of partons or two-gluon exchange model, or it can also be the photon as it was used in Jesse's talk. And the point is that we want to measure the leading protons in dedicated detectors that are usually placed at very high rapidities, so very far downstream in the direction of the beams, and they have to approach very closely to the nominal beam. So for that we use usually the technique of Roman pots because we want to preserve the vacuum. So again, the AFP detector is placed on both sides of the Atlas interaction regions at around 200 meters. The outermost stations, they are equipped with I will not speak about the silicon tracker, but the two outermost stations are equipped with the time-of-flight detector. Why? Because when we want to measure the diffractive processes, we very often have the case that where we have a false signal signature, which is depicted here in the top plot where we want to we just want to demonstrate what is happening. We can have simultaneous signals in the forward detectors, which are indicated with the red points and red arrows, and then we have a central system that is measured by the central detector, and this mimics the topology that we want to actually have in our centrally double diffractive processes. But we can use the time of flight method to suppress the contribution of such background, and it is based on a measurement of time in the two on the two sides. How does this work? Is actually very easy, because if we measure the time of one of the signals on one side and on the opposite side, if they really came from single production vertex, the times measured on one side are advanced or retarded with respect to nominal time, and we can deduce then what is the position in Z along the beam axis of that production vertex. So this is something that is shown in this space-time diagram, which you can see here, where the bunch crossing is depicted that has a dimension in the Z in the space and also in time. This diagram also shows why it's not possible to measure just one the time in one arm or on one side to infer the production vertex, because then we would need to know also the time of the production vertex itself. So we would need central timing. The time of flight detectors are Cherenkov detectors. The Cherenkov light is produced in quartz bars. We call them LQ bars because they are L-shaped. They are placed just behind the silicon tracker, and they are segmented in a matrix of 4 by 4 pieces of the LQ bars, and so we have a which you can see on the picture, on the lower picture. We have 4 channels. We call them A, B, C, and D, and 4 trains of channels for which we use the numbering from 0 to 3. So we have such a segmentation of the detector, and the detector is mounted to multi-anode microchannel PNT. And the processing of the the processing of the signal looks as it is indicated in the diagram above. So we have the protons that are entering the LQ bars, producing Cherenkov photons, which then enter the MCP PMT. The signal from the MCP PMT is amplified and goes to a constant fraction discriminator. This element is there to provide a timestamp, actually, the timestamp of the signal, and constant fraction discriminator is used because the amplitude of the signal can be very different between events, and then we process the signal in time to digital converter, and then we have the measurement of time. So the first thing to study in the 2017 data was to measure the efficiency, which is measured in a very straightforward way. We have a data sample where we require to have tracks in the silicon tracker in regions of interest that are overlapping in acceptance with the trains of the time of flight detector, which is indicated here in the plot, and we can measure then the efficiency of registering a signal in each of the channels. We used a few runs from the 2017. One was with some time gap between them also, and in different conditions as concerns the amount of pileup that we had. And I will now present the result from this first run, this July run. In terms of these plots, so what these plots are showing is the efficiency in single channels in the far A station and far C station, so the left and right side from the interaction region. And then also the plots are shown for the situations where the track was pointing to actually. So the first plot, the very left and top plot shows the efficiency when the track was found to point in to the first train, and the efficiencies are then measured. But we can see that we also see some non-negligible efficiencies or signals in the neighboring channels, which is mainly due to production of secondaries. So this is the we can see that the efficiency of the whole train, so the combined efficiency of all 4 channels in the illuminated trains is around I don't know 6 up to 9% in the far A station, and it's a bit lower in the far C station, around 3 or 4%. And this was in July. If you look to September, to run that was recorded in September, the efficiencies drop already to 5 and to 2% or 3%. So we can summarize this in plots where we show the train efficiencies from July and from September, and we see a drop between July and September. And what we also see in September, we used another run which was taken just after the first run in September, which was at higher mu. So we see that there is a drop between July and September, and there is the efficiency is not sensitive to the level of pileup, because the last run, which is actually of quite low statistics, has considerably higher pileup, but the efficiency is not sensitive to that. So and we blame the drop in efficiency. We blame the PMTs to degrade proportionally to the time of exposure of PMTs. So then another task was to measure the single channel resolutions, time resolutions. So for that we use a topology of events where we require to have the signal only in one train of TOF. So this is different different from the previous case, where I also allowed to measure the efficiency in the channels that were neighboring to the train that had the track pointing to it. But now here we limit this the topologies to have the signal only in one train, because we learned that the efficiency, the time resolution is then the best. So we have a single channel time that looks like this. It's proportional to the arrival time of the proton. There is some constant delay specific to each channel due to length of the cables, and then there is a random component that the width of which we want to measure. It's this TI smear, and then we measure the time with respect to LHC clock. What we use, we use one channel as a reference for another channel. So we need to have at least two hits in each train to construct the distributions of time differences. And from the width of the time differences, we then infer on the values of the single channel resolutions according to this formula that is minimized. So the measurement is the sigma ij, and we want to extract the values of sigma I and sigma j. And we also have the correlation. We may have a correlation between the channel times due to charge sharing, but this we treat as a systematics. So what are the channel resolutions?
Carol, you have 2 minutes. Yeah.
Okay, thank you. So we measure the channel resolutions that are actually very good. They are almost always below 50 picoseconds. There is a systematic shape of these resolutions, this U shape, and we know that the first channel actually has a low photon statistics, so it can be explained by that. And the last one, the last channel, has the thing that it shares less signal with the neighboring channels on the PMT, and then we can also expect that there will be a slightly worse measurement. And this also applies for the first channel as well. So we think we understand the shape of this. But although the efficiency was quite low, the time resolutions were very good. And then last thing was to actually to try to make a proof of concept of the time of flight measure method. So for that we used another run which had a moderate or quite low pileup, and we compared the position of the primary vertex with the values obtained from the time of flight system. And you can see the distribution of such a observable the difference between the z positions of the vertices, and we see an indication for a signal there. And we also extracted the single channel resolutions in this run again, and we use that to predict what the expected resolution should be, and within the error the width of the signal is consistent with the expectations. We fixed the background fit in this low statistic sample quite well by using an event mixing where we mixed events from different events to produce the background shape. So conclusions: the efficiency was rather low, caused by deterioration of the MCP PMT. The resolutions were actually measured at very reasonable levels. And vertex matching analysis showed that what we observe is consistent. What would we expect? Thank you for your attention. Thanks.
Super. Thanks very much, Carol.
Thank you.
Okay, I'm sure you have questions for him. So for this shutdown, do you plan to do anything to work on the
yes, there's a better person to comment on that, but yes, the main improvements are concerning the PMTs, and also the optical part is going to be changed. The LQ bars that are used that were used in 2017 were glued together using an optical glue. But now they are manufactured in a new way that no glue is used, so it's a single piece LQ bar, and the new PMTs, and also the PMTs will be placed in not in a secondary vacuum. There are many changes that are going to be applied.
Okay. Thanks very much. But the actual quartz bars themselves, the radiators are not the limitation at the moment. It's the efficiency of and the longevity of the PMTs, right?
I would say yes.
Actually, let me comment here very quickly. If we get a Pico TDC, then the construction of LQ bars is really the most limiting factor, because contributing to the resolution.
Okay, thanks very much. And this LQ bar consists of two materials, if I understand correctly, with this mirror to transition between them. Is that correct? Or it's one material?
It's one material. It will not only be glued from two pieces, but just one single piece.
Okay. Thanks very much.
Thank you.
Any other questions for Carol? No.
Sorry.
Okay, no, it's okay. Well, I think we can also take this to the Mattermost.
Okay.
So now we make a switch from Atlas to CMS, and I'm pleased to introduce our colleague from Torino, Ada Solano, and Ada will present the performance and upgrade of the precision proton spectrometer and the performance of the proton reconstruction for the CMS experiment.
Thanks a lot. I will try to keep the video if it stays.
Okay.
Okay, sure. Okay.
Thanks.
I hope you see.
Perfect.
Okay, I only have a problem with this. Okay. Okay. Good morning, everybody, and thanks for the presentation. I will present you the precision proton spectrometer of CMS, its performance, and the upgrade program for LAC Run 3. Here, you see the outline of the talk, but let me draw your attention to the sketch below of the PPS detector, which is placed on either side of CMS along the LAC tunnel at about 200 meters from the CMS interaction point. Here you see the LAC tunnel with the movable structure called the Roman pots, which allow to insert the detectors very close to the beam inside the LAC beam pipe. PPS was born as a joint project of the CMS and Totem collaborations for measuring scattered protons at very small angles in standard LAC running conditions at high luminosity. In the PPS physics program focuses on central exclusive production, which means some processes in which the protons remain intact and can be measured in PPS, and the central system X produced in the interaction can be measured in the central detector of CMS. Protons lose only, scattered protons lose only a small fraction of their energy, and can be measured with detector very close to the beam. PPS has tracking and timing stations. The tracking detectors are used for measuring the proton fractional momentum loss C, and in general, the proton kinematics, thanks to the knowledge of the beam optics, while the timing detectors, which measure the time of flight of the protons, are used to disentangle the pileup in order to identify the interaction vertex biased by timing technique. The experimental challenge of PPS is to go with the detectors to a few millimeters from the beam, about 1.3, 1.5 millimeters, to maximize acceptance. So the detectors must tolerate high levels of non-uniform irradiation. This means for 100 inverse femtobar, which is almost that of run 2, a proton fluence of up to 5 × 10⁻15 protons per centimeter square, which corresponds to a dose of around 160 megarad. Challenging are also the spatial resolution required, 10-30 microns, depending on the coordinate, and our goal for the timing resolution of 20-30 picoseconds. PPS took data during run 2 with different configuration depending on the availability of the detectors. We started in 2016, 1 year in advance, with the Totem detectors to prove the feasibility of running a near beam spectrometer in high luminosity conditions. Then in 2017 and 18, we've been running in our standard configuration very stably, as you can see from the fraction of data collected with respect to CMS, integrating a total of about 115 inverse femtobar during run 2. Before going to the performance, let me say a few words on the detectors, but since I do not have so much time, please look for more details in the backup slides. For the tracking detectors, our baseline technology is that of 3D silicon pixel sensors, which ensures radiation hardness, high granularity, and slim edges. In run 2, we had those with the columns etched from both sides. We have also used the silicon strips from Totem. For the timing detectors, we have been using diamonds, single and double diamonds, but also in 2017 a plane of ultra-fast silicon detector. Ultra-fast silicon detectors are also used by Totem in their vertical Roman pots. Vertical Roman pots are not used by CMS, which only uses horizontal pot, but vertical Roman pots are needed for the alignment of the apparatus during special alignment runs a few times per year. Here you can also see how the timing resolution allows to disentangle the primary vertex from pileup. And this is needed if you remember that during 2018, the mean number of pileup events was about 35, and we know it will grow. For introducing the performance of the tracking detectors, let me show you the heat distributions in the tracker stations, 2 per side from the interaction point. In 2017, we had the strips and 3D pixels, while in 2018, in both stations, there were 3D pixel detectors. You can clearly see that the heats are concentrated very close to the beam. The distribution is very peaked, which translates in a highly non-uniform irradiation and so radiation damage. I'll start with the strip detector. 2 major sources of inefficiency have been studied separately: radiation damage and multi-track capability. The first one is here radiation damage. This detector built for Totem were not supposed to stand these high proton fluence. And indeed, we have changed them a few times during the run in technical stops to recover the efficiency of the detector. You clearly see the degradation close to the beam. And this is also shown in this plot, where the efficiency is shown as a function of Xi. So it degrades at low values of Xi. And here is computed separately for each of the main LHC crossing angle used in 2017. In the right plot, you see the drop of the efficiency as a function of pileup. Since these detectors have not the capability of reconstruct multi-tracks. For reconstructing multi-tracks, clearly a pixel detector works better. We have chosen 3D pixel sensors, bonded to the PSI-46 digital chip of the central CMS tracker. And here you see the evolution of the efficiency maps for the pixel detector as a function of the integrated luminosity. In 2 stations, 1 per sector. These are the most far station, and here is plotted only the region of which is most interesting close to the beam. You see that in general, the efficiency is very high. The degradation is close to the beam, very peaked. And this is not due to the sensor, but is due to the chip, and in particular to the non-uniform irradiation of the chip. We had studied this problem in a specific irradiation campaign, so we were ready to it. And to mitigate this problem, the Raman pots were shifted twice in 2018, each time by 500 microns. And this is why you see that the damage region it becomes wider in the vertical position. To release the efficiencies for physics analysis, they have been measured for different integrated luminosity in the different run periods. Here you see an example of the efficiency at the beginning and at the end of the data taking for the FAD pot of sector 5-6. You see the degradation in Xi. Let me say that the interval of the in Xi of the PPS detector goes more or less from 0.02 to 0.2, depending on the closest approach of the detector to the beam and on the aperture limitations. To better follow the the efficiency variations in the critical region, an irradiation peak area has been defined, for which you see the measurement of the efficiency done every 1 inverse femtobar in the critical region. You see the drop and the recovery of the efficiency due to the vertical movement of the Roman pot during the technical stops. I should say that outside the integration peak area, so in all the rest of the detector, the efficiency remains constant and greater than 95% during all data taking. Let me now move to the timing system, the timing detectors. We have used diamond detectors, one station on each side of the interaction point, each station with 4 diamond planes, 2 single diamond and 2 double diamonds. Double diamonds have been measured to have a better resolution of a factor 1.7 with respect to single diamonds. Here I show you the measurement for the full station. So a lot of work has been done.
2 minutes.
Thanks.
2 minutes.
For calibrating the detector, and here I only show the final results, so with everything included, so sensor front end, digitization, calibration, and reconstruction procedure. What you see is the proton timing resolution in the tooth sector for 2018, depending on the sector, and as a function of the integrated luminosity, the resolution goes from about 90 picosecond to about 125 picosecond for a selection in which one track in both pixel stations is required, and all 4 diamond planes with 1 pad each fired. And so one can say that timing detectors with this performance can be used for physics and can give an important background reduction. My last slide on our upgrade program for LAC Run 3. PPS will operate as a full CMS subsystem. The tracker system will still have 2 Roman pots per side, with a new 3D silicon pixel sensor, this time produced in single-sided technology and embodied to the PROC600 chip of the first layer of the CMS central pixel tracker. We know that this chip has the same problem with respect to non-uniform irradiation. So we are implementing an internal movement system for the detector package with these piezoelectric motors to better distribute the radiation damage. There will be 12 positions spaced by 500 microns with the possibility of handling more than 50 inverse femtobar without minimal efficiency loss. Also, the timing system is undergoing an important upgrade program, both on the electronics and on the sensor. And moreover, we are planning to install a new timing station in each sector. So we will have also 2 timing stations per sector. Each station will have 4 double diamonds planes, so that we think that with 8 double diamond planes in each sector, we will be able to reach our ultimate goal of 30 picoseconds. So conclusions, I hope I've convinced you that PPS has proven the feasibility of continuously operating a near beam proton spectrometer at high luminosity. We have collected 115 inverse femtobar of good data during run 2, and we will go on during run 3, for which we are pushing a program of upgrade. Let me add 2 more things. Studies in the past years of a PPS detector for HLLAC have recently converged into an expression of interest draft endorsed by CMS and sent to the LACC. So if you are interested, stay tuned. And of course, last but not least, we have a rich program of physics analysis. I could not say a single word, but let me at least point you out to this talk by Justin Williams last Tuesday at this conference on a recent and interesting analysis for a search for exclusive diphotons with intact protons, which allow to set limits on the 4-photon anomalous quartic gauge couplings. Thank you very much for your attention.
Thank you very much, and a very, very rich talk. Lots of details on covering different technologies. Okay, I see already Tom has a raised hand. If anybody else like to ask a question,
yeah, please. Ada, if you go to the slide 10,
yes,
and then to slide 11. So here we see the resolution. So do I understand correctly? The resolution deteriorate in the time?
Is the proton timing resolution for the 2 arms? Yes.
Yes, and it's time dependency. So it deteriorate starting from.
Yes, sure. It depends on the integrated luminosity. Yeah. This is okay. I have something in the backup slides. We also see a slight deterioration of the diamonds with the integrated luminosity. Maybe I can go to it. I don't know if I have time. But anyway, you can have a look at yourself.
I will have a look. So my question was,
and but okay, so it's not that big, but then it is convoluted with also the electronics and so on, and so in the end, okay, there is a slight degradation. Yes.
Okay, and then I mean, if you go page 11, it's a fantastic. I mean, you would like to have 2 timing stations on
yes.
both sides. It's really beautiful. I envy you, I would say. Still a question concerning the resolution. So let's say you have 80 now. You
yes, 8 double diamonds, all double diamonds. So yeah. Double diamonds are 1.7 better than single diamonds. So we think that, and also there is a very important upgrade program also on the electronics. Okay. This also you find in a backup slides all the single points on the electronics that are subject to the upgrade, and we think this will allow to go to this resolution.
Thank you. Still in this direction. I mean, so imagine that you have you mentioned that you can use timing detectors with 80 picoseconds for the physics program, for the background suppression. My simple question is where I will find any study in this direction showing this effect, because sorry, here I have some doubts about 80 picoseconds can help you even in a run 2, and not talking about run 3. With a better than 30 picoseconds, it can it's a different story. But I'm interested in some physics studies. So can you please give me a hint, even via
I have to say that there are notes on timing resolution coming out. I could not show you the final results because they are not yet approved, but you get your answer in a while.
Thank you very much, Adam. Thank you.
Thanks very much. Thank you, Tom. So we're out of time, unfortunately. I also have some questions regarding the difference between sector 5.6 and 4.5 and how this improvement in the mechanics will allow you to adjust the detector position and how that will work in an operational sense. So but we can do that on Mattermost,
yeah. But the idea is simple. So instead of just moving the Raman pots during the technical stop, we will move internally the detectors.
Yeah. Okay. So you won't need any realignment or anything like that? No,
because there will be... I mean, part of the first alignment, then the movement will be internal to the pot. So you will keep knowing the relative movement.
Okay. Thanks very much.
It can be calibrated, of course.
Okay. Thanks very much. That makes sense.
Thank you very much.
Okay. I think we need to unfortunately close this session. There's the coffee break coming up. And maybe I leave it to Jerry to let us know when we should come back.
Yeah, we are unfortunately late, but I think that we still need like 5 minutes break, at least for toilet and these things. So, okay, so we will be back in 10:05, so in 5 minutes, and the second part of the session will be chaired by Prafula. Thank you very much.
Yes.
Hello, please, Dr. Jin Yifan or Yin Yifan.
Yes.
Yeah, I still cannot see your presentation uploaded to the Indigo.
Yes, that's true. I'm actually doing it now. Can you hear me?
Okay, perfect. Yeah,
Thank
I
you.
can hear you.
Yes, I'll do it now. Mm-hmm.
Okay, thanks. Okay, Prafula, I think that we can start.
Okay. Let me welcome back the session after coffee break. This session we have 6 talks and ranging from Atlas, CMS, and again Bell. So each speaker allotted 15 minutes. So we'll stick to the same time allocation, and 12 minutes for the talk, 3 minutes for the question and answer. So I will give reminder at after 10 minutes of the talk, and please stick to the time allotted. So let's start the first talk of the session by Sosi Suna from KK. He is going to give us an update on the operational experience on the Atlas pixel detector. Please.
Okay, can you hear me?
Yes.
Hello? Yes?
Yes,
okay.
Yes.
Right, okay, then let me share my screen. Can you see it?
Yes.
Hello?
Yes.
Yes.
Okay. Okay, so I'm gonna give a report about the operational experience for the Atlas pixel detector through the run-through experiment. Go to the next slide. So maybe I think I don't need to introduce about the Atlas detector itself, but for the pixel detector, as you know, this is located on the most inner side, and there are 2 naming. There's one thing we need. I need to remind you that there are 2 naming scheme about a pixel detector. We have 2 different pixel systems. One for the pixel was since used in the run 1. Then the other pixel was the new pixel detector introduced in the since run 2 experiment, which is located in the very close to the most inner side on the beam pipe. So we have a 4-layer system in the barrel and 3-layer system in the end cap disk. Go to the next slide. So first of all, this is the outer pixel detector was used in since run 1. This is the original one. That spec of this pixel detector is consist of the NEN sensor with a dimension of the 60 by 60 with the 250 micron thickness, then with the 60 AFES front end on the sensor. This consists of the about 1744 modules surrounding the beam pipe, which consists of the 80 million channels, and this output the 8-bit time over threshold. This was designed for radiation tolerance of the 1 times 10 to 15 neutrino equivalent, which corresponds to the 50 mega radiation for the electronics. Go to the next slide. Then this is a new pixel detector installed in the since run 2. We call this is the IBL. This was the named as the insertable B layer. This detector was quite new since run 2, and more superior spec from the outer pixel detector. Now this IBL detector itself has the already 20 million channels with the smaller pixel size about twice smaller than the outer pixel, and it's more radiation hard, 5 times hard than the outer pixels, which is the 5 times 10 to 15 neutron equivalent, 250 megalarc. So as shown in the bottom 2 plot, this is a performance with and without this new detector. Blue, this left-hand side plot shows the performance of the B tagging. Blue is the without IBL, and red is with this new detector. You see that in the same efficiency point, almost we got 10 times better rejection power. And also right-hand side plot is the resolution of the tracking as a function of the momentum. You see visible difference, about twice better than before. Go to the next slide. So with 2 detector in the operation-wise point of view, we have 2 different ways to manage this operation. So as you see in the LHC Run 2, that the accelerator makes a big effort and to make the large luminosity. That peak luminosity is already twice higher than the design value, which makes us very difficult for the old readout system in the outer pixel detector. On the other hand, we also have a new detector, IBL. This was the first time to operate such a high radiation environment. So we also need to accumulate the more knowledge to how to operate the new detector. So we need an experience. Then in the end, later of the Run 2, radiation damage is more severe, especially for the B layer. This is a second innermost layer, which is the old one, was already close to the final, already close to the design radiation hardness, which is halfway already, 5 times 10 to 40. So this makes the some efficiency degradation. That I will show in the later slide, that becoming already visible. In the next slide. So here is a operation overview. I cannot explain for the experience through the Run 2, but typically our pixel detector or Atlas detector operating on the about 100 kilohertz at the hardware level 1 trigger and recording the 1 kilohertz at HLT, which with the about 55 pi-lap interaction per event. On the other, but the Pixel has operated very well, almost achieving the 99.5% data quality efficiency through the Run 2. So here, plot showing the some record how the readout error occurred as a function of the time through the 2015 to 2018 or 2017 in that case. So first of all, beginning of the Run 2, as you see, this is monitored by the synchronization error in the readout system. If the timestamp is different in the collision data and the pixel detector, that makes some synchronization error. We monitor this such an error rate. Then if that error rate is more than 10%, for instance, that is a really critical limit. We lose the data. So here we see some profile how the error is controlled. In the beginning of the 2015, and somehow that error rate is about a few percent level, even though luminosity is low. Then continuing this is the 2016. Then 2017, in the middle of quarter 1, after quarter 1, we introduced the some mechanism how to control the readout error. That makes us reduce the readout error drastically. Then later we also improved some detector itself. So in the end of the Run 2, even though we have a high luminosity, we in the end we controlled such an error rate less than 0.1% level. So now I'm going to explain what was done for run 2 as the operational experience. First of all, we made some readout upgrade in the older pixel system. So as I mentioned, in the outer pixel detector operating on the old readout system, that the new IBL detector, which is a bit slower to read out the current LHC conditions. So, so this table shows the upgrade schedule. First, we have a serious problem in the layer 2. That is only record the data in the 40 megabps. That was urgently necessary to upgrade as soon as possible to the 80. Then sequentially, we made some upgrade up to the 160 megabps. That was a twice faster readout. Then we also introduced the resynchronization machinery, which is the kind of the refresh of the event counter at the front end level. So right hand side plot shows the how the error rate is reduced or suppressed. So starting point is the black one. Then each upgrade, that error rate is drastically reduced. Then in the end, finally, we achieved around red marker point. So this was a big upgrade. This is as a function of the trigger rate. So this was a big achievement for the hardware side. And also, we take the same readout firmware system with the IBL new detector, so that all the detector is now synchronized coherently use the same software, so that makes easier to debug and maintain the performance. Go to the next slide. So then another. Yeah.
Oh, yeah, you have 2 more minutes.
Okay. Then the other point is the bilayer threshold evolution. As I mentioned, radiation damage is serious, so that we also deal to the sometimes raise up the threshold, but at some point we also have to reduce the threshold due to the radiation damage. So first we raise up the threshold. This is due to the readout problem, readout limitation, but later in the end of the last year, we go lowered the threshold down to the 4,000. So here, right-hand side plot shows the tracking performance. In the end of the 2017, we have some degradation, about 60%, but during the lowering the threshold, that efficiency is recovered. Now, radiation damage is becoming more serious, impact on the depletion voltage. That was frequently monitored by taking the high voltage scan. And this table shows the evolution of the bias voltage, looking at the IBM starting from the 80 volt, but now we are operating the 400 volt, which is 5 times higher already. And the right-hand side plot is the high volt scan as a function of the bias voltage. You see that the plateau is not appeared already, but still we keep try to keep the higher operating point. So this was probably a serious big issue in the run 3 operation. Now, other point is we also met this some optoboard problem since the beginning of the run 2. This optoboard, this is the optical fiber link from the on detector to the off detector. That failure device is broken as a function of the time, and at some point increasing. The plot showing that failure rate is increasing. So this was we lose the signal so that we urgently need to replace this optoboard link that was located on the surface of the inner detector. Now, next slide. This is a summary of the hit-on-track efficiencies through the full run-2 experiment. As I said, the innermost layer and the secondmost layer, the efficiency is degraded as a function of the time, but at some point this was recovered due to the lowering the threshold or sometimes replacing the hardware, fixing the readout system. Then on the other hand, layer 1 and layer 2 is still manageable level, but we already have some experience how to recover the efficiency. Then next slide, some weak structure is still observed from the IBL. This is mostly comes from the single problematic module, likely from the SEU event. So I explain in the later slide. Then next slide 13 is the fraction of the inactive module. This is correlated to the hardware upgrade and how the synchronization method is implied. So you see some fluctuations here and some improvement in the end. This is how we had in the current detector. Then last point, this is probably a more important topics in future. This is a single event upset, single event effect. We have two effects, one from a set single event transient, which hits the logic circuit and makes the false signal in the memory. And SEU is, as you know, the bit flip of the by the direct interaction in the memory chip. This was observed first in the global register, showing the top right-hand side plot. We see some deep structure here, then during the time, but at some point we, after refresh the global memory, the low voltage current is recovered, synchronized the occupancy is also recovered. This is a proof we observed single event upset, a single event effect. Then we set the refresh mechanism. First, reset the global memory every 5 seconds. Then second, we refresh the global memory, pixel register every 11 minutes per cyclically. So bottom plot shows the impact, how the occupancy is recovered from the single event effect. So as a summary, we made an experiment. We see the excellent performance over the run-2 and high granularity, high quality data quality of more than 99.5%. And we also gained experience how to recover from radiation damage and how to overcome the readout limitation issue. For run-3, radiation damage will be more severe, and we require some fine-tuning of the operation parameter. And also in the simulation side, we are planning to employ the radiation damage simulation for future in run-3. I think that's all.
Thank you, Suno-san. So, any questions?
Yes. Sorry, maybe you have mentioned this already, but I would like to ask, what is the current situation with the IBL, and if the problem with the TID peak that was observed at the beginning is completely off now, or there are still some issues connected with this?
TID is another issue that originally we thought that that TID is a saturator above 1 megalat, but we still see some drift future. I don't know how it still keep going, but still keep continuing some tuning is still necessary.
Okay, but you are probably very well after the behind of this TID peak, so it should be better now.
Yeah, it should be better now. Of course, yes. Yeah, no, of course, we pass away the peak. Yes.
Okay. Thank you.
Okay, thank you, Suno-san. So we are running out of time. Maybe we can take more questions on the Mattermost. Thank you, Suno-san, for a nice update. And we'll move to the next speaker. Next speaker is Benjamin Nachman from LBNL, and he's going to give us an update on the modeling of radiation damage to pixel sensor in Atlas detector.
All right, can you hear me and see my slides?
Yes.
All right, fantastic, thank you. So let me go right ahead. If I can advance, there we go. So you heard just a talk from Soshi right now, who gave an excellent introduction to the Atlas pixel detector and the operational conditions. So I won't spend basically any time talking about that. Just as a reminder, here's a picture of where our detector sits at the heart of the Atlas detector. And today I'm going to focus about how we can measure radiation damage effects. So you heard a bit about that radiation damage effects already from Soshi. Great. So I don't think I need to spend much time with this audience telling you what radiation damage does to our detectors. But I wanted to highlight a few things before I get into the main part of the talk, which will be about leakage current. So just to remind everyone, we're talking about hybrid pixel detector, where we have focus here will be about the sensor damage. And in particular, the non-ionizing energy loss, which will damage the silicon lattice and causes defects which act as traps for charge carriers. And there are multiple impacts of these defects. So in particular, the electric field is deformed inside the sensor bulk. And this plot on the top left shows the electric field as a function of depth. This is in simulation, where you can see the different colors correspond to different points in time. And there's a significant modification to the electric field as we go from the beginning of run 2, for instance, to the end of run 2 for these, or to the end of 2017 at least, for the IBL sensors. So in addition to the deformation of the electric field, there's also an increase in the depletion voltage and the sensor leakage current, and that's what I'll spend most of the talk discussing. But one thing I did want to mention is about the collected charge. So these traps, they can reduce the amount of collected charge that's deposited by, for instance, a minimum ionizing particle. And this plot on the top left, if you focus just on the red or the dark orange color, this shows the cluster charge on the IBL, the innermost pixel layer, as a function of time in run 2. And you can see this sort of continuous decreasing trend, which corresponds to more and more charge being trapped as the more non-ionizing energy loss is accumulated throughout run 2. And this, of course, has a broad impact on physics, which I'll maybe briefly touch on at the end before concluding. But the radiation environment inside our detector is really extreme. So this plot on the left shows the fluence as a function of z and radius. So it falls roughly as 1 over r squared. And the innermost layer, the IBL, has experienced a significant amount of radiation. And I think everyone's familiar probably with the units that we use to measure the fluence, which is the non-ionizing energy loss, in units of 1 eV neutron equivalent. And for the pixel detector, most of the damage comes from primary hadrons, in particular charge hadrons. And as you go further away from the interaction point, the contribution from neutrons is more prominent. And this plot on page 8 shows the fluence as a function of time since the start of run 2. And the upshot is that we've accumulated something like 1 times 10 to the 15 neutron equivalent per centimeter squared in our innermost layer. And the red here is the innermost layer, and the other 3 colors here correspond to the outer layers. As Soshi noted, the innermost layer was inserted in run 2, so it starts at 0, the red starts at 0 and goes up, and it crosses the other layers in 2016. And sort of being able to determine the radiation damage is really critical for informing many aspects of our experiment, in particular operations, offline analysis, and of course, designing future detectors. Okay, so we measure the fluence. We can measure the fluence in many ways, but the most common method is to use a leakage current, which is proportional to the fluence, at least over short time scales. And so here's how we model the leakage current. So we measure leakage current on the left is delta leakage current. If it starts at 0, then the delta is the leakage current at a given time. We want to know, for instance, what the fluence is and the relationship for a given integrated luminosity, how much fluence do we measure. And the rest is the V is the depleted volume, which we assume is a constant, which I'll come back to in a second. And then the rest models basically the time dependence that's due to annealing. Okay, so here's a plot that shows for the outer 3 pixel layers, so the so-called B layer, layer 1, and layer 2, the leakage current normalized to 0 temperature, 0 degrees Celsius as a function of integrated luminosity. And you can see a comparison between a prediction from the various models. So a model of the generation of the particles, the interaction with the detector, and the damage to the sensors, and their conversion to leakage current, which is using the Hamburg model. You can see really excellent agreement across the whole time, at least for the shape. The overall simulation here has been scaled in order to show just the shape. Okay, one of the key challenges here is that, as I mentioned, we're correcting to 0 degrees Celsius, so the temperature is not constant as a function of time. And in order to make this comparison, we have to correct for the temperature dependence. We correct for the temperature dependence, which is known, and it depends exponentially in this way on the temperatures to go from a given reference temperature, go from a given temperature to a reference temperature. And one of the nice measurements we've made recently is we've tried to basically determine the most important parameter in that equation, which is E effective. So E effective tells us how we can convert between, for a given reference temperature to a given reference temperature. And this is determined using temperature scans. So the left plot here shows the top panel, the temperature on a given module as a function of time. And you can see we've basically stepped the temperature through multiple values. And so with these data, we can measure the current and we can apply a correction. And basically we can determine the correction to the temperature. So based on this E effective, that makes the corrected current independent of time. And that should be the correct E effective that basically allows us to remove the temperature dependence. And so this E effective, of course, is known from the literature, but there is quite some uncertainty. And so we wanted to measure it in situ, and the bottom right shows the extracted E effective for all of our layers as a function of Z. And you can see it's roughly consistent across the layers, especially the outer layers. And also we have 2 measurements in different points in time for the IBL. And there's a systematic shift between the IBL, the innermost layer, and the outer layers. And there are a variety of sources of uncertainty. The error bar here comes from the biggest source of uncertainty, which is that there's basically degeneracy between the measurement of the E effective and the temperature on the sensors. And so there's some unknown offset that is hard to determine in situ. And also the black open and close points, which are a bit hard to see on this plot, but if you zoom in, you can see there's a systematic shift there. It's very small between different points in time. And this is something where we're still trying to understand to see if there's some time dependence. Okay, but given this value, we can plot forward to then extract the fluence rate for all the layers. So this plot shows as a function of Z, the fluence rate. So that is the conversion between integrated luminosity and fluence for all 4 of the layers, the pixel layers. So the black one is the IBL, the innermost layer. So innermost means more fluence. And the most striking features of this plot are that if you look at the black, the points have a much stronger Z dependence than the prediction. If you go to say 40 or the end, which is between roughly 30 centimeters, you see that the black data points are about a factor of 2 below the prediction. And if you look at the outer layers, you can see that the data points are systematically above the predictions. And that's not true for the innermost layer, but it's true systematically for the outermost layers. And at Z equals 0, the effect is not small. So it can be up to 50% or so. So one thing we've been doing recently is try to put this in the context of the full inner detector, at least the silicon part of the inner detector. And so now what I'm going to basically spend the rest of the talk discussing is how the pixel detector measurement sort of fits together with the rest of the silicon-based inner detector. So now we'll have plots that look like this, where you can still see the 4 layers of our pixel detector, but now you also see the strip detector, the SCT at the bottom, which is further away and therefore has lower fluence. But the interesting observation is that, as I mentioned before, so at Z equals 0, the data and simulation are about the same for the innermost layer. Then it's about 50% higher for data for the outer pixel layers. And then for the strips, it's basically back to being about the same, which is a sort of an interesting Z-dependent trend. And you can also see that the radius-dependent trend, and you can see that the Z-dependence also in the strips is pretty spot on for the predictions. Okay, so here's another way of looking at exactly the same information. So now as a function of rapidity, or pseudo-rapidity instead of Z, there's sort of a nice way to see the fiducial acceptance of the inner detector. You can see basically have a tracking acceptance up to about 2.5. And in this range, it's kind of a nice way of looking at it because the particle production is roughly constant as a function of superrapidity. And so you might expect something like roughly constant damage, although we can see like on the black points that there's a much stronger Z dependence, which is now quite clear at high rapidity.
Hi, Ben. Two more minutes.
Thank you. All right, so one other way of looking at these data is now as a function of radius. So before it was a function of Z for a given layer. Now you can see basically for each of our layers, there's 4 pixel layers and 4 strip layers in the barrel. And you can see the data points and the prediction. So each point corresponds to for a specific color corresponds to different values of Z. So you see there's a really big spread in Z for the innermost pixel layers, and then the spread gets smaller as you go to as you go further out because the Z dependence becomes smaller. And you can see roughly this 1 over R squared trend. What you can see sort of nicely in the strips is that our 2 simulations here, which correspond to different transport models, so Geant4 and Fluka, sort of nicely bracket the data, which is not so much the case on the innermost layers. But you can see this sort of nice overall coherence between the innermost and outermost layers. Okay, so that's basically all I want to say for now about the leakage current and the measurement of the global picture of the radiation damage within our silicon-based interdetector. And I want to end just by saying that this information is really critical now for many reasons, but one of the most critical inputs is for our offline simulation in order to make various predictions for physics analysis. And so one thing that Sochi alluded to at the end of his talk is that we've now integrated fluence modeling into Atlas simulation, which will be default in run 3. And the most important input is the fluence, which we've now measured on all of our pixel layers. And this very complicated looking graph basically describes the impact of radiation damage on our digitization, where we model this charge trapping I mentioned at the beginning, and its influence on the deformation of the electric field and the resulting loss in signal, which I don't have time to discuss in detail, but you can follow the link at the bottom of this slide for more details. Okay, that brings me to the end. So the fluence is really a key ingredient to radiation damage modeling. We performed a very detailed measurement using leakage current, not only for our pixel detector, but also coherently within the whole silicon-based interdetector, including our strips. And this has been integrated into the radiation damage, into the simulation of Atlas. And this is just one teaser plot that shows from Atlas simulation what is the cluster charge for various points in time. And the point is that we have the 4 pixel layers, and you can see the charge changes as a function of time because of radiation damage in our simulation, which can be partially recovered by changing, for instance, the high voltage. So you can see that the charge drops and then goes up and then drops again. And the jump up is because of increasing the high voltage. And this structure will be, of course, very important for improving data analysis in run 3 and also planning for the high luminosity upgrade. All right, thank you very much.
Thank you, Ben, for the nice detailed result on the radiation damage for the pixel detector Atlas experiment. Any question to Ben?
Maybe I would have a question. First of all, thank you very much for this presentation. I remember that you are not in the comfortable time zone now. I'm sorry for that. And my question is probably stupid, but you mentioned that the measurement of the temperature of the sensor is critical for these models. So how actually are you determining the sensor temperature? Because it is definitely not easy to measure it.
Right. So we have on module NTCs to measure the temperature, and so we have a very fine in space and time measurement of the temperature. But there can be an offset between the temperature reported in the NTC and the actual relevant sensor temperature. And this offset, which we just don't know what it is, it could be a couple of degrees, which would explain the error bar here, I think, is 2 degrees, if I remember correctly. And so you can see kind of what a 2-degree shift would do to this measurement.
Okay. So is there, for example, a way how to determine this offset, like in some lab measurement or something like this?
Exactly. So this is something we want to follow up on. I mean, in principle, one thing we have studied is you could imagine simultaneously extracting the E effective and the temperature offset. In principle, if you look at you can't tell from the equation, but they're actually not degenerate. In principle, one could do it formally. However, in practice, they're basically degenerate, so it's not possible to extract that in situ. But yeah, so there's two possibilities. So one is to try to do some simulations to see if we can learn something about what the offset would be. And the other is to do some lab measurements. Even those are a bit difficult, but indeed, this is exactly what we want to do, to try to pin down what the value is.
Okay, perfect. Thank you.
Okay. So for me, one more question. There was some kind of estimation of the depletion depth using Lorentz angle measurement. And is it still you monitor the depletion depth as you go on the radiation, and that is how you go with the voltage change, bias voltage, or you don't?
Right, exactly. So I didn't talk about depletion voltage. So she mentioned it a little bit.
Okay.
We have multiple ways of monitoring the need to change the depletion voltage. But yes, the main one is using these we use the high voltage scan. It's not the Lorentz angle as the primary way of doing it. But yeah, we monitor with the high voltage scans where we measure the charge collection efficiency basically and its saturation. And so on this plot, the reason I picked this plot is because you can see on the bottom panel the high voltage basically, and so all the jumps are because we noticed that we need to increase based on the high voltage scans. And in fact, in 2016 we noticed that our innermost layer was running under depleted actually, and this was noticed both in the high voltage scan but also in the leakage current, because if you look at ratios of leakage currents, you can tell that right. So we know that ratios of leakage currents for the same Z should be constant, and they're not. It wasn't our same radius should be constant. It wasn't constant, and so that told us that we were under depleted basically, and so we fixed that, and now it's constant. And the other rises are because of high voltage scans.
Thank you. Okay, thank you, Ben, for nice talk, and we move to the next speaker. Next speaker is Patrick from DEGI. He's going to talk about the alignment of CMS tracker.
Hi, can you hear me?
Yes, please share.
Okay, I will share the slides.
Yes, fine. Good.
Okay. Thank you for giving me the opportunity to present the work about the alignment group of the CMS tracker. So my name is Patrick. I joined the CMS collaboration end of 2014, and among other activities, I'm taking care of the alignment of the CMS tracker, and today I'm very proud to present the result of our group. So let me go to a quick introduction, a quick reminder about the CMS tracker and the concept of the silicon modules, where the resolution is around 10 microns. You can see a figure representing 1/4 of the phase 1 detector. You may know that at the end of 2016, the pixel was upgraded from phase 0 to phase 1, but the strip hasn't changed. So our detector is roughly 5 meters long and 2 meters of diameter. It's the largest silicon detector in the world in size and granularity. And we have around 20,000 modules. So we have two challenges basically with the alignment. So after the mechanical alignments, we have a precision on the position of the module, which is 1 order of magnitude larger than the track resolution, the hit resolution, sorry. And then modules and substructures are moving with time, and we need to ensure a constant response of the detector over time. Here I'm only talking about the CMS tracker alignments. There was a presentation by Yun Yong yesterday about the muon chamber alignments, which I point you here. The purpose of the alignment is illustrated by the two figures on the top of slide 3, where you see on the left what you think your tracker is doing, and in the center what it really looks like. Basically, the alignment consists in determining the position, orientation, and surface deformation of the roughly 20,000 sensors of the CMS tracker. And we must include the time variations, and then we must perform the alignment during the data taking on short time scale and after the data taking to reach ultimate precision. So that means roughly 200,000 parameters at least if you want to do a precise alignment. So the scope of this presentation is to present the general strategies and the performance of the alignment of the central silicon tracker, especially with regard to data. And the techniques presented in this presentation are, I think, of large interest, not only for alignment of other types of detector, but as soon as you have a large number of parameters in your problem. Let's go to the general concept of track-based alignment. slide 4. So basically, we minimize the same chi-square as when doing tracking, except that we also release the alignment parameters, which are here denoted with P. And at CMS, we use two algorithms. One is millipd, which actually is independent of CMS, but CMS has been a driving user of millipd, where we release all alignment and track parameters simultaneously. And another algorithm is called HIPI, and there the procedure is done iteratively, where P and Q are fitted separately. Of course, we have a few challenges. One is that we have an extremely large amount of parameters. So both algorithms linearize the chi-square, and then we utilize tools from linear algebra and numerical analysis to reduce the problem to something achievable in a reasonable amount of time. And then we have several issues. We have potentially non-physical distortions arising from internal symmetries of the problem. This is what we call weak modes, as I mentioned earlier in this session. So they denote invariance, non-physical transformation of the geometry. Another problem are variations of conditions over time related to, for instance, changes of temperature or magnetic field. And then last, we also have a strong interplay with the local reconstructions. So we are very sensitive to the aging of the detector over time of the modules, of the silicon modules. So let me first describe a little bit more the weak modes. The weak modes correspond to any transformation that don't change significantly the chi-square. So it means, in other words, that it changes a set of valid tracks into another set of valid tracks. So a helix will stay a helix, for instance. And that arises, among others, from symmetries of the detectors and symmetry of the collision track topology. Two examples are shown in the middle. On the left-hand side, you can see a telescope weak mode with R varying proportion to delta Z, and in the center, a twist weak mode. To constrain weak modes or to control weak modes, you need to use special track topology. And for this, we use two types. At CMS, we use resonance tracks, which allow to constrain modules in different directions instead of only constraining modules in the neighboring of the tracks. And another is to use cosmic rays, which are vertical tracks just breaking the symmetry of the detector. A third possibility would be to use beam halo. They would be analog to cosmic rays, but horizontal. We are currently not using them, but we are investigating its feasibility at CMS or maybe for a phase 2 detector. And then we need to accumulate as much as possible resonances and cosmic rays, and they will play a crucial role in the quality of the alignments. Time variations, there are several causes for affecting on the alignments. We have magnet cycles and temperature variations. The former mostly affects the large mechanical structures, and the latter affects, introduce some noise at the module level. And then we also have the aging of the module, which I already mentioned. We are working in very high radiation environments, and the change of Lorentz drift inside of the silicon modules should in principle be covered by some dedicated calibration, but it's not entirely the case, and part of it is absorbed in the alignment. So we have two solutions to face the time variations. One is to apply during data taking, which just consists in realigning as often as possible with, of course, limited statistics of special track topologies. And the second is applied for end of year or so what we call legacy reprocessings, where we have more time to perform the alignments, where we want to realign the whole year. And there we introduce a hierarchy and align separately the absolute position of high-level structures, which can mean different things with time dependence, and the relative positions of the modules to these high-level structures without time dependence. And that is a compromise to include time dependence while avoiding splitting samples of special tracks. So the high-level structures can mean different things, but typically they can mean subdetectors like barrel pixel half barrels, for instance, something like this. Now let me go to the alignment during run 2. So we have two things to discuss. First, the alignment as startup and the alignments all along the year. So at the startup, what we do at the beginning of the year is to align just with cosmic tracks. The top left figure shows the average rates of cosmic tracks at CMS. Effectively, the track rate is of 2 Hertz. And with cosmic tracks, we try to align high-level structures before first PP collisions, at least in the pixel detector. Each year, roughly half of the cosmics with magnetic fields are taken during commissioning. Now we also take some 0 Tesla cosmics, and if sometimes we have enough statistics to perform alignment at the module level in the pixel, and that is, for instance, what we did at the beginning of 2018, This is still limited statistics, but this is enough to already improve significantly the performance of the alignment. And bottom left figure is illustrating this case where we compare the performance of reconstruction of the subtracks of a cosmic track traversing the whole detector. And then you can see that using the old geometry from 2017, we got bad results or large differences between the track parameters of the subtract. And with a realignment, we get much better performance. Then we use first collision tracks. We must react very quickly in order to avoid time-dependent alignment, which means which also means more delicate configuration. But then we suddenly have much more statistics, so we can improve the statistical precision of the alignment. Of course, at this point, we still don't have any resonance data, so the Z going into 2 muons, so full module alignment is still difficult to achieve in the whole detector. Along the year, then we try to avoid having to derive the alignment by hands, and we try to set up some automated alignments. So once we are confident in the alignment that is being used to record the data, we activate the automated alignment. This is what is shown on the right figure in white, where we show the movements of the half barrels along X in the barrel pixel. And the idea is to align as soon as possible with the most recent data, with very simple collision track data, so without special track topology. Of course, we can only align high-level structures, so mechanical structures, so that we avoid having too large number of parameters, and we only align in the pixel. So that can be derived and applied in less than 48 hours, so at a very high rates. And however, there is one limitation: we cannot correct for radiation effects, in which case custom alignments has to be derived manually and deployed manually. This happens, for instance, when we change the calibration of the local reconstruction of the pixel, which is shown by the dashed vertical lines in the trends. Let me move on and go to the so-called legacy reprocessing, which was the last very large campaign that we did to rederive the whole alignment constants. Slide 9. So you may know that the CMS collaboration decided 2 years ago to perform a whole reprocessing of the data covering nearly the whole run 2, so from 2016 to 18, corresponding to roughly 114 femtobarns. For the alignment group, that meant around 1 year of intense work to produce the ultimate run 2 alignment. So let me give you a few points about this campaign. So what we did is to align each year separately, but in a single and global fits, in order to accumulate enough cosmics, since this is the limiting factor, but in the same time, we could not group 2 years together because differences are too large. We were able to cope with the residual systematic changes in heat positions due to the radiation, thanks to an appropriate hierarchy of alignment parameters. I will come back to that point in a few slides. And we did, in this context, the largest alignment fits to date in terms of number of parameters to align with up to 700,000 parameters. I think that's our record. All in all, that means we have around 220 geometries over the 3 years to cover the significant changes over time. On the right-hand side, you can see my favorite picture showing the successes of the alignment in the legacy reprocessing, where we look at the invariance mass, the invariant mass of the diamond system as a function of the outgoing muon kinematics. Of course, this should not depend on the outgoing muon kinematics. This should just correspond to the mass of the Z. But if you see some systematic pattern, this indicates systematic misalignments, typically weak modes, here the twist weak mode. And then you can see that the green curve, the legacy reprocessing, is performing way better than the former realignment. This figure, of course, doesn't include further momentum scale correction beyond the alignment. This is only showing changes related to the alignment.
Patrick, 2 more minutes.
Yes, thank you. Then, of course, when you do tracker alignment, what you want to check is, of course, quantities related to tracking and vertexing. This is shown here on this slide. I show on the top left tracking performance, the bottom left vertexing performance. I show here 3 arbitrarily chosen geometries taken from 2017, and I compare them to some Monte Carlo, which we try to derive with average performance between the different data geometries. In the top left, what we do is that we measure the residual of the hits belonging to a track each time we fit it without the hits under scrutiny. So you expect here a distribution peaked around 0. Let me tell you, that will be important for the next slide, that we can perform this separately for inward and outward pointing modules. I will come back to that point on the next slide. And then you can see that we have nicely peaked distributions. Then on the bottom left, here we can see vertexing performance. Here we'll measure the impact parameter of tracks belonging to a vertex each time we fit it without the track under scrutiny. And here we expect some flat distribution around 0. You can also find such a distribution where we compare with former reprocessings in the backup. Let me then go to the interplay with local reco. So I told you that we can do the tracking performance, that we can measure the tracking performance for inward and outward pointing modules separately. This is important because the local reco is affected by accumulated radiation. So the radiation corresponds to the gray arrows in the sketch in the middle, and basically the arrows will be changing over time. And the alignment is sensitive to changes in the Lorentz drift induced by radiation accumulated at a scale of around 1 inverse femtobarn, while the pixel local reconstruction calibration can only be performed every roughly 10 inverse femtobarns. And for that reason, the alignment needs to absorb residual effects due to the accumulated radiation. So the barrel pixel modules are arranged in ladders facing inward and outward. Hence, the systematic shift that is implied in the tracking performance will occur in opposite directions. And this is what this figure here is measuring. Delta mu is the difference between the two peaks of the distribution measuring the tracking performance. And for instance, in the alignment during data taking in blue, you see that we were not correcting for that, and this delta mu is getting larger and larger over time, while the green is very close from 0. And that is one of the great successes of the legacy reprocessing. Last but one slide, further results. Here just a selected figure, again the invariant mass now shown as a function of the azimuthal angle of one of the outgoing muons. This is taking only one of the 220 geometries. At first order, we just fit with a sine curve. And then we show the amplitude of the sine as a function of process luminosity on the bottom left. And then you can see again, comparing the same geometries, that while we had strong differences in the alignment during data taking, we managed to reduce them very strongly for the legacy reprocessing. So this has a direct impact on the reconstruction of muon tracks, especially at high PT. And yeah, we interact a lot, of course, with the physics group, especially muon physics object group at CMS, and they of course were very, very happy to see these improvements, and they directly see an impact on physics. We have tons of other results, which I put in the backup about movements of modules, overlap of modules, impact parameter trends, alignment errors, BPX barycenter. We have tons of results, which I invite you to take a look at and to ask me questions offline. And now let me go to the summary and conclusions. So I presented the general concept of tracker alignments, namely track-based alignments, time variations, intrinsic symmetries, and interplay with local reconstruction. I presented strategies during and after data taking very briefly, and then we see very nice improvement of the alignments performance with the legacy reprocessing, including flattening of the Z-Boson mass distributions, track-it residuals, impact parameter, and so on and so forth. Again, there's an extensive amount of results in the backup, which I invite you to take a look at, and we are preparing a paper with all this material. Thank you very much for your attention.
Thank you, Patrick, for detailed presentation. And we can take a quick one more question, please. Tom?
Tom is speaking. If you go to the slide 4. So yeah, thank you. So you are saying extremely large amount of parameters. So related question. So how many? But basically, what are these parameters? I mean, this is a position on the sensor or whatsoever. So exactly. What are the parameters, just to get a feeling?
Exactly. So thank you for your question. We have the position, the orientation, and surface deformation. So that means 8 or 9 parameters per module, depending on whether you take modules in the pixel detector or in the strip detector. And if you neglect time variation, that means roughly 200,000 parameters. If you include time variation, then we have different cases. I don't enter in details here. That can go up to 700,000 parameters. And that is only the alignment parameters. Of course, I'm not talking about the track parameters, so the QJ. I'm only talking about the P.
Thank you for answering my question. And probably also yours question related to TOF presentation, because in our case, the number of parameters is orders of smaller. So, yeah. Thank you.
Yeah, we can discuss further offline your case on Mattermost.
Yes. So, thank you, Tom. So let me thank Patrick for his presentation, and for the question we can take up with the Mattermost. And we're running out of time, so we can move to the next speaker. Let me welcome Subhankar for giving a presentation on the material budget in the CMS tracker. Please, Subhankar.
Hello, can you see the slides?
Yes, please.
Maybe I'll go to the presentation mode. So just give me a moment. I think now you should be seeing it in full screen mode.
Yes.
Okay, thank you. So good morning, everyone. You'll be presenting a method of estimating the tracker material budget with the triplet method. And the results that I would be showing today is based on, is extracted from the data collected by the CMS experiment. So this method is called the method of triplets. And today it uses 3 consecutive hits along a reconstructed track, and it measures the sagitta in this system and extracts the radiation length locally from the scattering angle. So 3 hits, and hence the name triplets. And this procedure allows for accurate and granular measurement of the material budget of the tracker. And so why do we want to measure the material budget? Is because that the estimation of the material measurement in the tracking volume is a key ingredient for precisely measuring the momentum, which in turn is required for measuring precision quantities like, for example, ongoing effort on measuring the mass of the double boson. And so today, the results that I would be showing is using the data collected by the CMS experiment in 2016. And I would be only showing the results from the CMS pixel detector. And we will draw the comparison between the material that is measured in data and the one that is in simulation. And we have used 1 million tracks for this analysis. A quick overview of the CMS tracker. So this innermost region has the pixel detectors. So this is actually the phase 0 CMS tracker. So just a warning that at the end of 2016 and 2017, the CMS pixel detectors were replaced. And so the current CMS pixel tracker has 4 barrel layers and 3 end-cap disks. But we will focus on the phase 0 detector. So the more important picture for us for the discussion that is following is on the picture on the right. So we would be using information from the 3 pixel layers that is in the barrel and the innermost outer tracker, which is called the tracker inner barrel, or TIB. And for the others, the outer tracker is comprised of the TOB, and which is the tracker outer barrel, TEC tracker end cap, and TID. We would not be discussing results from those today. So the track selection. So for this analysis, we select tracks between 0.75 GeV to 1.5 GeV. And the lower threshold is to reject tracks that would not traverse the entire radial length of the tracker. And we require that the tracks should have at least 14 hits, because we would like to reuse the same track to build triplets, combination of triplets for in the entire tracking volume. The relative uncertainty on the transverse momentum in measurement should be less than 1%. And we do this measurement in beans of eta and z for each layer in the barrel. So now coming to the description of the method of triplets. So I'll draw your attention to the figure on the right. So here what I'm showing is a trajectory of a track that is crossing 3 layers. And the hits in the 3 layers are marked by V1, V2, and V3. And what we assume is that the scattering happens in the central layer, and we define a system using these 3 points, defining the vectors A and B. And with some calculation, we can show that if we take the radius of curvature rho as rho for this track, and as I said, the scattering angle to be theta, the sagitta multiplied by the transverse momentum can be expressed with the formula that is described here. So we call this quantity, which is Pt times S, the sagitta, as T. And as you can see, this comprises of 2 terms. The first term on the right, which is Pt over 2 rho, is constant for a given system of triplets, while the second term is Pt theta by B, which is dependent on the multiple scattering angle in the central layer, which is the layer N on the figure on the right. Now, the expectation value of theta is 0. So the expectation value of the term T will depend on the expectation value of the first term. Okay. So now let us inspect the first term in more detail. So the Pt over 2 rho, instead the Pt can be expressed as 0.3 b rho over 100, and it would change sign depending on the sign of the track. So if I simply replace the expression of Pt in the first term, so it would turn out to be 0.3 b over 200, and here b is measured in GV. Sorry, the Pt is measured in GV, V in Tesla, and rho is measured in centimeters. So simply replacing all these and assuming and taking B to be 3.8 Tesla, the first term turns out to be 5.7 10 power minus 3 GV per centimeter. And on the right, we show the plot of the quantity T for a system of triplets where the heats are in the barrel pixel layer 1, layer 2, and layer 3. In blue is points are from Monte Carlo, and the red ones is the red line is from data. And as you can see, for both signs of the track, the expectation value is 5.7 10 power minus 3 GV per centimeter. And today I would be discussing results from 2 systems of triplets where heats are in BPX layer 1, layer 2, layer 3, which represents a figure on the left, and on the figure on the right, it comes from a system of triplets where the heats are in BPX layer 2, BPX layer 3, and TIB layer 1. So what we can see is that in both the systems, the expectation value of T is around 5.7 10 power minus 3 GV per centimeter. Only thing to notice is the difference in the overall normalization between the left and the right plot. This is because the distance between the distance between the BPX layer 2 and TIB layer 1 is much larger compared to the distance between BPX layer 1 and BPX layer 3. Hence, the plot on the right has an overall higher, say, Y scale. So what we are interested actually is now the width of these peaks. And so the spread of the distribution of T is governed by the spread in theta, and which is given by this formula here, where x over x0 is the thickness of the scattering layer in terms of radiation length. And if we write out the variance of T that I expressed, explained earlier, it can be written out as a combination of 4 terms. And we neglect the contribution from the first 2 terms because it's their contribution is about 1 order of magnitude smaller than the last 2 terms. And so in order to separate the contribution of the third term, which and the one from the multiple scattering, which is the fourth term, which is the term we are more interested in, what we do is we plot the variance of T as a function of Pt square. And at pt equals to 0, the only contribution to delta t comes from the variance of theta. Now, from the formula above, the variance of pt theta over b can be expressed as a constant 0.0136 over b whole square multiplied by the radiation length in that layer. So now what we do is for each beam of eta, so for example here it's we have taken the beam of eta between 0 and 0.2. What we plot is the variance multiplied by b square as a function of pt square. So on the left is a plot coming from data, and on the right is the one coming from Monte Carlo. And we do a straight line fit to this distribution, and we take the intercept at pt equals to 0. And this intercept for each beam would give us the material budget in that particular beam. So now coming to the radiation length that is measured for BPX layer 2. So
Shubhankar, 2 minutes. Huh?
Yes. Okay. What you see on the left is the traversed material budget for BPX layer 2. So you can see that as you move forward in higher eta, the track is traversing a larger amount of material in that particular layer, and so the radiation length increases as you go higher in eta. On the right is the same radiation length, but it is weighted with the sign of the polar angle of the track. So essentially, you are measuring the radiation length in a direction perpendicular to the beam, and hence, and you see that it becomes flat as a function of eta. Whereas here on the next slide, I'm showing the same results with BPX layer 3, and on the left is the traversed material budget, which shows the same feature that was seen before for BPX layer 2. So if you go higher in eta, the material budget is increasing. The interesting feature is in the plot on the right. So if you see that even after weighting with the sign of the angle of the track, for the innermost part, which is, let's say, between -1 and 1 in eta, it becomes flat. However, after that, it starts to increase. So this is the effect coming from the fact that in this region, the support structures and the cables that are present between the barrel pixel layer 3 and the tip are also contributing to the measurement, and hence you see this increase in the radiation length. So this brings me to the conclusion of my talk. So I presented today a new method of estimating the material budget of the CMS tracker with 1 GeV tracks. And the radiation length was measured in data and simulation for the pixel detector. And what we noticed is that the distribution of the material in barrel pixel layer 2 is almost flat when you weight with the sign of the angle of the track, while for BPX layer 3, it starts increasing for values of eta greater than 1. And as I said, this effect is because in that region, the approximation of constant material is failing, and the material of the cables and cooling adds to the measurement in those beams, and this is weighted by the distance of that particular material from the central layer. And with CMS is aiming for several precision measurements with the full runtime data, and the precise estimation of material budget can be a key ingredient for momentum calibration, and because the momentum measurement is affected by the material budget in the tracking system. So what we are doing is to validate this model also with the strip detectors for the CMS tracker, and for the studies are planned for the data collected by the CMS detector in 2017 and 2018, where the geometry is slightly different. And what I would like to point out is that the method can be easily implemented in any silicon tracker with the geometry which is similar to the CMS tracker. And at the end, I have a few references for documentation on this method. So this brings me to the end of my presentation. Thank you for your attention.
Thank you, Subhankar, for your detailed presentation. Any question to Subhankar?
I would have a question. You certainly plan to use this method also for the new tracker built for high luminosity LHC. So are you already doing some simulations for this new tracker design?
I mean, you mean that whether we have done some analysis with the simulated phase 2 geometries? No, at this point, no. We would like to first concentrate on finishing up the studies with the phase 1 CMS tracker, because that would be more crucial for the upcoming, let's say, analysis with full run-to data. And after that, we will see if we can proceed to phase 2 as well.
Okay, so in this case, how the radiation length of the new tracker for high lume LHC, how it is calculated in a different way, or because definitely you are calculating the radiation length?
Yes, I mean for that simply there are tools to compute the radiation length using on what the material that is description of the present in simulation on. So you simply add up if you draw, let's say, tracks along a particular eta or z, you simply add up the amount of material that track is passing through.
Okay, sure. So that would be probably a nice cross check if you will apply your method.
Yeah, of course, yes.
Okay, thanks.
Okay, thank you, Subhankar, for your presentation. So we are running out of time, so maybe take few questions on the Mattermost. Please follow on the Mattermost, and we'll be also following all the questions. And let's move to the next speaker, Joshua, for giving the presentation on the precision luminosity measurement in CMS. Please.
Yeah, can you hear me? Hello, everyone. Let me quickly share.
Yes.
Okay, do you see it full screen?
Yes, we do.
Okay, thanks a lot. So hi, everyone. My name is Joscha. I'm at DESY, and on behalf of the CMS collaboration, I will present our results for the Run-2 luminosity measurements. For an introduction, as most of you probably know, luminosity is a measure of the collision rate in a collider experiment. So the higher the luminosity, the more collisions we have, and thus the more events for any specific process we have. So if we want to measure the cross-section of a process, we count the number of events and then divide by the luminosity to get the cross-section. And because of this, having a precise luminosity measurement is a crucial input to any cross-section measurement. And I just put here a reference to the target precision for high lume LHC of a luminosity precision of better than 1%. And there was a talk on Tuesday going a bit more in detail about this and how we want to achieve this detector-wise. Now, if we measure luminosity, we can first do that using only beam parameters. So if you look at the sketch on the lower side, you have a number of protons coming in from the left, another number of protons coming in from the right. They cross at a frequency f in a transverse luminous area that I call a luminous here. If you know these properties, then you can calculate the luminosity by the formula given on the upper right-hand side. However, in general data taking conditions at the LHC, the determination especially of the luminous area is not very precise. So to get a precision luminosity measurement, we take an alternative route, which is a two-step procedure. First, we calibrate the detectors that we use for the luminosity measurement, which means we measure a reference cross-section in a special LHC setup where we can determine the luminous area precisely. And then we integrate the rate measurement of this detector over the whole data taking period and normalize it with the calibrated cross-section to get the integrated luminosity. So what I'm going to talk about is how we achieve precision both in calibration first and then in integration. But before that, let me give you a quick overview of the luminosity detectors at the CMS experiment. First of all, we have two special luminosity detectors, PLT and BCM1F, which are in the forward regions close to the beam pipe. Then we also use some of the main subdetectors of the CMS experiment. So we use the tracker for pixel cluster counting, PCC, and for vertex counting, as well as the muon drift tubes and the forward hadron calorimeters. And finally, we can also use the Ramses radiation monitoring system to get an estimate for the luminosity. Okay, so for each of these detectors, we first want to calibrate the rate measurement of these detectors. And for that, we use the Vandermeer or VDM method. The VDM method relies on special LHC fills with a low pileup in which we perform VDM scans, in which we separate the beams transversely and then move them in steps across each other. We then measure the rate as a function of the beam separation, and this is the plot on the right-hand side. And we do a Gaussian fit to this data, and then we get the width of the distribution called cap sigma x here, which is the width of the luminous region along the scanning direction. And then we repeat a VDM scan in y as well, and then we have the width in x, the width in y, and the product of these two gives us essentially the luminous area. So having this, we know we can compute the luminosity during VDM scans, and then we can use the peak rate, R0 here, to compute the visible cross-section, so the cross-section for the rate measurement in our detector. Now, the question is, what is the precision of this? So we have several ingredients. First of all, we have the proton numbers that we need to know, which we get rather precisely from LHC devices. And then we need the cap sigmas. So there we need to know the rates and the beam separation precisely. So the rates, for example, have to be corrected for backgrounds. And then one important consistency check that we do is that we not only have one pair of VDM scans, but several. So the lower left-hand side, for example, shows the visible cross-section for pixel cluster counting for several successive VDM scan pairs in 2018, where we find a nice agreement. Now, the next two slides are some of the main uncertainties here. The first slide deals with the beam separation. So with the x-axis on this plot on the right-hand side. So if we go to slide 5, the beam separation is at first order derived from the magnet settings of the LHC. These are the nominal positions of the beams. And we want to calibrate the length scale of these nominal positions by comparing them to measured vertices with the CMS tracker. This is called the length scale calibration. The plot is on the upper left-hand side, where we essentially have the measured vertex position as a function of the nominal position. And then we get a slope, and this slope is applied as a correction in the VDM fit. In addition to this linear behavior, we can have that the beams move away from the nominal orbit in a time-dependent fashion. This is an effect that we call orbit drift, which we monitor with LHC beam position monitors. And an example from 2017 is shown in the plot on the lower left-hand side, where all data points are at a head-on period, so where the beams are nominally head-on, and you see that the beams move by something up to 20 microns in such a fill, and we monitor this and then correct the VDM fits for that. And the third effect here is the electromagnetic interaction between the two proton beams. These are the beam-beam effects, which we typically apply as one is the beam-beam deflection. So we have an electric repulsion between the two proton beams, which increases the separation depending on the initial separation of the beams. So this is shown on the lower right-hand side. And then we also have what we call the dynamic Bether-Star effect, where we have a change of the shape of the proton beams from the focusing and defocusing due to electromagnetic interactions. This is applied as a correction to the rates and is currently under re-evaluation because we underestimated some stuff there in the preliminary results that I'm showing today. And finally, we're coming to the most important systematic part of the calibration, which is the factorization bias. In the VDM method, we make scans in X and in Y, and then we multiply them to get the luminous region. This assumes that the beam shapes factorizes in X and Y. However, in general, that is not the case. We have some small X and Y correlations so that this simple product doesn't give the full story, and we have a small bias in the calibration result. So to correct for this bias, we reconstruct the transverse proton beam densities using measured vertices with the so-called beam imaging method. And the results, the run 2 results are shown on the lower left-hand side. These are the estimates for the factorization bias for the different VM scans. And you can see that the effect can be larger than 1%. And for example, in 2018, 13 TeV proton-proton collisions, our systematic uncertainty is 2%. So this is a huge uncertainty. And to be able to tackle that better, we are currently developing additional methods to bring down this uncertainty. So one is that we implemented offset scans, which are VDM scans where we additionally separate the beams in the non-scanning direction. So if you look at the plot on the right-hand side, you have in red VDM scans, rate as a function of separation in X and in Y. And then in blue, you have offset scans, which are additionally separated in the non-scanning direction, meaning we test a different slice of the luminous region and are thus sensitive to the X-Y correlations. And another thing that we are investigating is to look at the beam spot evolution, so we can estimate the center and the width and other properties of the beam spots measured with our tracker, and analyze the evolution as a function of the beam separation. Okay, once we have done all this and have a precise calibration of for each of the detectors that we're using, we integrate the rate measurements. And there, two effects are important. The first is linearity. Because the VDM scans are done under special conditions with a very low pileup and a large bunch crossing spacing, and we have to extrapolate the visible cross-section from these conditions to the regular data-taking conditions. This is called linearity. And one example of an effect is afterglow, which is a spurious signal that we get from the activation of detector material after collisions, which is then measured in the time slots of the following collisions. So the upper right-hand side shows a plot where the first half is filled bunch crossing, so there's actual collisions and the rate measurement, and the right-hand side shows empty bunches. So there are no collisions, but we still get a rate measurement, and we can use these empty bunches to estimate the afterglow and derive a correction that we can then apply to the filled bunches as well. After correcting linearity effects for different detectors, we can make cross-detector comparisons to estimate residual nonlinearity. So the lower left-hand side shows an example of the ratio between different detectors as a function of instantaneous luminosity during one example fill in 2018. For example, if you look at the purple dots, these are two detectors, the ratio between two detectors, and this is a nice linear curve. So there is some nonlinearity between these two detectors, and we can fit this with a linear function, get a slope, and if we collect all the slopes from all the fills, we get a distribution like in the lower right-hand side, and we can use this to estimate the uncertainty due to residual nonlinearity. Then we have stability, which deals with the change of the detector conditions over time. So we have VDM scans once per data taking period, most of the time means once per year. And if the detector conditions change over the year, then of course you have to take that into account. An example is in ICHEP, the forward hadron calorimeter, we have a gain loss from aging in the PMTs and fibers, and this changes the response. A powerful tool to estimate this are emittance scans, which are short VDM scans. And in 2018, we had them at the start of every fill and at the end of many fills in the CMS experiment. And from each of these scans, we can get a rough estimate of the visible cross-section and then thus monitor how the efficiency of these detectors changes over time. And the upper right-hand side shows the results from the emittance scan analysis for ICHEP for 2017 and 2018, when we can clearly see how the efficiency changes, and we use this to derive correction. And after we corrected all stability issues for all detectors, we can again do cross-detector comparisons. So the lower plot shows the ratios between 3 detectors for 2018, where you can see that there is some evolution in the stability of the different detectors, and again use this to assign an uncertainty. So we have calibrated and integrated our rate measurements, and then we get the run 2 luminosity for proton-proton collisions at 13 TeV to be 139 inverse femtobarn with a relative uncertainty of 1.8%. The two parts contributing to the uncertainty are the calibration with VDM scans, where the largest uncertainty comes from the factorization bias, where in the future we'll have additional methods to improve the precision. And the second part is the integration of the rate measurement, where we have linearity and stability effects, whereas linearity effects are slightly larger. These are all preliminary results, so we have a lot of improvements already underway, so we can soon expect new results, updated results with uncertainties of better than 2% per year. Thanks a lot for your attention.
Thank you for the presentation, and maybe you can take a few questions.
Yes, please.
Maybe I would have a question. So you just mentioned that there will be some improvements. So at the moment, this total uncertainty, is it important or like a critical uncertainty for these absolute cross-section measurements?
Yes. It depends, of course, on the cross-section measurements. Examples are the TT bar cross-section, where all other systematic uncertainties combined in 2016 are 2.5%, as is the luminosity uncertainty. And we have in the pipeline a few W and Z cross-section measurements where the relative impact of the luminosity is even larger. So there are a lot of cross-section measurements which are really looking forward to the improved results.
Okay, thanks.
Okay. If there is no more question, maybe you can move, thank Jose for his presentation, and maybe we can move to the next speaker, EFN Jen, who will speak about the diamond detector in Bell 2, measuring the radiation and beam abort.
Yes. So hello,
please share your screen. Yes.
Let me share it. The first one. Okay. Can you see it in full screen?
Yes.
Okay, thank you. So morning, everyone. This is the talk about the diamond detector on Bell 2. Oh, sorry, next page. Yes. So first, I will roughly introduce about the whole system of diamond, then introduce something about its functionalities. So this is our Bell 2 detector. So Bell 2 is now the luminosity frontier, and using Bell 2, we are aiming at searching for some physics beyond the standard model, and we hope we can accumulate 50 times the luminosity than Bell. So in order to reach this luminosity, we use nano beam technology, which here you can see a plot for the nano beam, and then we can reach an instantaneous luminosity at this value. So when we have this much higher, much intense luminosity, it is also saying that the radiation maybe will be more severe than before. So in order to protect the Bell 2 subdetectors and also to protect some components of the accelerator, we installed a diamond on this region on the Bell 2 near the induction point to serve as a beam abort system and a radiation monitor. And this is the picture of our diamond. So the diamond sensor is here. It's very small. You can see the zoom out picture. It's just attached here on the beam pipe. And this is the beam pipe, which again is in the center of the Bell 2 detectors. So the diamond detector is actually just a solid state ionization chamber. It measures the current of electrons and holes produced by the particles that those stray beams. So here we call it diamond because the sensors are diamond. And it has actually a few very good merits here. The first is those diamonds, they have excellent radiation hardness because the Bell 2 is going to have a lifetime roughly 10 years. So in order to serve for 10 years, radiation hardness is very important. And the second point is diamond has very rapid response to radiations. So if some radiation burst occurs, we can record that immediately increase. And also, we don't need a very large crystal. We only need a small piece, as you can see here. It's a small one. And the last point is actually this crystal can measure a very broad range from micron rad per second to tens of kilorad per second. So for those reasons, we believe our diamond is very reliable and it's also a very stable one for a long-term dose measurement. And if we take a look again on the whole system, this is a picture. So up here is the inner detector of Bell 2. So in total, we have 28 diamond sensors, and 8 of them are installed on the beam pipe, which is here in the center region. And 4 of them are used for beam abort. The other 4 is just monitoring radiations. And we also installed 12 near the SVD, silicon vertex detector, which is actually at here the SVD cone. This part, the pink one, this one is SVD, and the remaining 8 is installed here near this brown one, which is the superconducting magnets. So the sensor is installed on Bell 2. Then we have a 30-meter cable sending the signals to our diamond control units. This diamond control unit, which actuates the readout electronics, is located in the electronics hut, which is like 10 meters away from Bell 2. So during the experiment, if anything goes wrong, usually the diamond is very solid. The sensor is solid, it should be okay. What if something happened? We just replace the readout electronics. And here, for this picture I show, you can see roughly this is the signal sent to amplifier, then digitized by ADC, then go to our FPGA. And FPGA will judge whether send abort or not. And the other side is to the computer through the Ethernet connections. And here also at the front end, I think I should mention that we have 3 ranges. In order to measure the current of different magnitudes, we offer here different configurations. And if we take a deeper look on this DCUs, this is shown here. So first is the ADC. It had a sampling rate 15 megahertz, quite fast. And then there is a memory buffer. So every 125 ADC value here are summed and then written in one memory cell here. So this memory buffer is running 400 kilohertz. And every 2.5 microsecond, let's say 400 kilohertz, is comparing the results in the memory cells. It can be the result of several cells or just one cell. It can be configured. And currently we set 2 thresholds. So for the first threshold, we call it very fast. This is checking in 4 memory cell, which is 10 microseconds. And we ask the radiation dose to be, the threshold is set at 4 millirad. And the reason for 10 microsecond is because this is actually the revolution time for the accelerator. And for those threshold value, we collect information from inner detectors or Bell 2, like the pixel detector and the SVDs. And then every time we check whether they get damaged or not, and then we lower down again and again. Finally, it evolves here, this value. Although we always lower it down, actually it's still quite high. You can see this is 100 times larger of the noise. So we are not going to be triggered by fluctuations. It's still quite a safe value. And the second threshold is the so-called fast abort, which is 1 millisecond for 40 millirad. And the last thing here is on the right side, this is to the computer side, all the data again in memory buffer are summed again and sent to computer at 10 hertz rate. So those rates can help us to estimate the long-term integrated dose. And here the last thing about the system is about its logic. So the abort logic here, we require a handshake. First is the diamond, if cross the threshold, will send here abort signal to the accelerator super KKB. Then super KKB receive our abort, it will send back a confirmation. So it's here. Of course, we have other beam loss monitors. You can see here on the right picture, we have a lot of them installed among the accelerator. So every time, initially, the diamond is quiet, then it's TTL high. Then if it fire aborts, it's go TTL low, which active low. Then until it's received back the confirmation from accelerator, then it will reset back to TTL high. And when it receives the confirmation, it will start to write down a memory file. And every time, if it's not the diamond fire aborts, it's other beam loss monitor, diamond will also, after receiving back the confirmation, will also dump a memory file. Okay, so let's see what the diamond can do. The first thing is here is the interface. This is an online interface. So when machine operators, they are tuned beam, they're operating, they always will take a look on these pictures. You can see here, this is the beam pipe. And based on the positions of those diamonds, those values are the dose rate of diamond. And it's easy to infer which beam, or whether it's electron or it's positron that need to be tuned further. So every time if the value gets increased, the color will change and they will pay attention on that. So the second thing is, if diamond already fires on boards, then it will dump some memory file. And usually we have 2 thresholds, so we have 2 quite typical radiation, let's say radiations. So the first one is very fast. You can see usually it's a rapid narrow spikes. It's like this, a very narrow one and increase very fast. And the second one is those continuous. So it's like a growing tail. It's just gradually increase, and finally the value crosses the threshold, then it fire aborts. So those pictures are also generated by the online software. So this is like a real-time reference. The machine operators always can track those pictures after there is an abort. And usually from this picture, we can also see some information. It's very interesting, like it usually takes like 27, 25 microseconds until it goes to 0, which means there is no more beam in the ring. And among our hundreds memory files, sometimes the memory file also records something very interesting. So the memory file usually it can record 5 seconds. And here is the zoom-in picture. And we can see there is the first peak, which actually already triggered abort. It crossed the threshold here very fast. But during the aborting, when the beam was getting aborted, there is a second huge peak. And this is quite dangerous one because you can see here the value is 700 millirad and our threshold is only 4 millirad. So this is the case that we should definitely prevent in the future. And of course, also we need to study what is the cause of those kind of quite dangerous situation. And let me show you also the figure about the abort statistics. This year, in the past 6 months, in total, the accelerator received 1,500 aborts. And Diamond fired 600 of them. And most of the Diamond aborts are the first type, very fast aborts. The second type, it exists, but very few, less than 10 times. And there is no forced abort due to the malfunction of firmware or whatever. Everything is fine, all the aborts are genuine. And this is picture is showing the births per day. So the blue one is per day, the orange one is total aborts number. So during machine studies, usually Diamond are very frequently sending aborts. It's like every hour, there will be around 10 Diamond aborts. But during the physics data taking, Diamond is very quiet. You can see we only get like 1 or 2 every day. That is also saying the machine operator can offer us very good beam conditions. And the last thing about Diamond is we have so many beam loss monitors, but actually if Diamond fire aborts, our signal is always, yes.
Hi, Jin, 2 more minutes.
2 minutes, yes. So we are always the first one to reach the accelerator. We are a very fast beam abort system. So this is a picture about the luminosity world record, which Super KKB achieved this year. And in June, this is a new record here. And a few days later, after a great effort of tuning, we get another even higher luminosity. So we are actually a protector. We are fast beam abort, so we can protect the Bell 2 detectors. And also we have other functionalities. For example, because we are measuring the dose rate. So if you integrate it, you get the dose. So this is the dose. Unfortunately here, this year, we have some damage on one channel, but now it's repaired. So this is integrated dose. And this integral dose of the superconducting magnets, which can help us to know whether in the future they will degrade their performance or not. It's always important to have an idea about how many doses have they endured. And other functionalities, like we can also infer the occupancy of the inner detector, SVD. For example, here you can see the yellow one is measured by SVD data. And here the pink one is the Diamond data give this value, and they're very close to each other. And their ratio you can see here is the ratio very close to 1. So the reason is when during injection, there is a veto window. So SVD do not read the data. So at this time, we can use the Diamond data to estimate the occupancy. And of course, for our other beam background studies, the Diamond dose rate is very closely related to the beam loss rate. This also can be used to study the beam condition. So in summary, our Diamond system is doing a very good job on protecting Bell 2 from radiation damagers. And we are very sensitive to 2 kinds. The first kind is those rapidly radiation bursts. Also, the second kind is the continuous radiations. And also our abort signal usually is the first one arrive at accelerator. We are very fast. And we also can provide a lot of information to beam tuning and for background studies. And also actually at this moment, we still have a lot of ongoing improvements, both on the hardware and on the software. Okay, thank you for your attention.
Thank you, Ethan Jane, for your nice detailed presentation on the diamond detector. So let's take few questions.
I have a question for you, Yifan. The material, the diamond material, who is your supplier for this material?
Oh yeah, sorry. Yes, I should mention. Sorry. Actually, I forget the company's name. Yeah, but I can later on the chat. I can write to you later. Yeah.
Okay, perfect. Maybe we can just discuss it on the Mattermost. Yeah, thanks.
Yes.
Congratulations for this system. Looks very stable. Yeah.
Okay.
So I just have one question. This diamond detector is going to last during the lifetime of the experiment, or?
Yeah, we plan to last until the end of Bell 2. We hope we can serve till the end. And this is not a problem because we have already do some R&D. How many doses can we endure? And based on the current performance of the accelerator, we think the dose is still okay. Our hardness can guarantee we can survive till the end.
Okay.
Good.
I would have also question. We had a presentation like 2 days ago from Felix Miller, and he was showing that there was already some damage of depth fed detectors. So was it already with these diamond detectors implemented or before?
Actually, there are several diamond groups at Bell 2. I'm not sure whether he's showing this because also we have other like cross detector. They also install diamond, and we also have some other diamond just measuring the luminosity. There are several parts. Our diamond is the SVD diamond parts, so that's why I'm on behalf of SVD. And our diamond is both beam abort and the radiation monitor. We do the two jobs.
Okay. So you like 100% believe that it will protect the inner tracker against, or have you already experienced some problem with this?
The only problem, like sometimes when there is some quench from the superconducting magnets, there will be some quench, and we make it a little impaired. Like you can see here, we lost the several channel. And usually the quick fix is we have some other spare. We just replace the electronics. But this year, the situation is a little tough. We don't have enough spare, and we shipping, although we ship there, but it's a little slow. So we still have one unrecovered channel here. But now it's covered. At this moment, everything is fine.
Perfect. Thanks.
Okay, if no more questions, then let me thank speaker Ethan Jane for the presentation, and we think we had a good session, though we had ahead of time actually. We spent a bit more time than expected. So we have a coffee break, and maybe if there is any announcement, Jiri can take over.
Yeah. Thank you. Thanks a lot for good work, Prafula. So now we should have a coffee break. It was planned to be like 20 minutes, but definitely we are well a bit behind of this. So we will have like 5 minutes only. So let's see each other at, we have 11:55, yeah? 11:55, then we will be only 15 minutes after the official schedule, yeah?
Okay.
11:55. Thank you.
Thanks.
And the chair will be Stefania.
Sure, yes.
Thanks.
Hi, this is Stefania speaking. Can you hear me? Maybe you can also see me. Yeah. So if there are any speaker who wants to try sharing and hasn't done this before, maybe Simon, you want to?
Yes, if possible, I'd like to check if you
Okay, thank you.
Okay, so I'll. So are my slides visible right now?
Yes, they are.
Very good. And the voice is also clear.
It is indeed.
Very good. Thank you very much.
Okay. If anyone else wants to try, we are here for you.
Hi, Stefania. Yes, I would like to try.
I hardly can hear your voice. I don't know if
is that better?
It's much better, yeah.
Zoom was changing it. Can you see the slide?
Yes, we can.
Perfect. Thank you.
You're welcome.
Can I quickly try it?
Okay, go ahead. Can you try speaking? Cyril, we can see your slides, but I don't hear your voice. Maybe you're not speaking.
Yeah, well, actually, when I share the slides, I don't see the monitor to unmute myself. I will go to the test room to be sure that I will be able to do that.
Okay, anyway, you have time.
It's typically on the top.
Okay, thank you.
Yeah.
Thank you.
Okay, it's 11:55. I think we should start the session with the last 7 talks. They are mostly from Bell 2 and LHCb experiments. And the first speaker is Kodai Matsuoka from Nagoya University, and he will tell us about the Bell 2 experiment. Okay, I don't know if you can maybe go full screen so we can see better.
Is it okay?
Yes, now it's perfect.
Thank you.
Go ahead.
Let me talk about the BEL2 experiment, status, and prospects. I'm Kodai Matsuoka from Kobayashi Masukawa Institute, Nagoya University. So the BEL2 experiment is a successor to the BEL experiment at the KKB accelerator, which collected about 1 inverse at band data. And the BEL2 plan to collect much more data, 50 inverse at band of collisions at and near option 4s energy. So we collide 7 GeV electron in the so-called HER high energy ring and 4 GeV positron in LER low energy ring. The key ingredient to achieve the 15 inverse at band data is a high luminosity realized by nanobeam scheme. So we plan to squeeze the beta Y star or the vertical beam size by a factor of 20, so 0.3 millimeter beta Y star compared to KKB, as well as increasing the beam currents. So our physics motivation is the following. So we aim to search for new physics in B sub-S D mesons and tau lepton decays. So we can also directly search for light new particles in the dark sector. Also, precise measurement of standard model and hadron physics are our also important program. in the BERT experiment. And the BERT collaboration is an international collaboration composed of more than 1,000 people from 26 countries and regions. The BERT detector is a hermetic spectrometer upgraded from Bell detector. It was designed to have a better performance even at a higher luminosity. That means a higher beam background and a higher trigger rate up to 30 kHz in the L1 trigger. So the detector consists of the state-of-the-art silicon vertex detector, the drift chamber for the tracking, and novel particle identification Cherenkov detectors called the top time of propagation counter in the barrel region and the aerogel rich counter in the forward end cap region, and electromagnetic calorimeters, and the K-long and muon detectors. We also adapt grid computing to process a huge amount of data. And the physics data taking with the full detector components started in March 2019. So we already identified some major issues in the beam operation. The most critical one is the detector lifetime, in particular top counter. That is because the quantum efficiency of the MCP PMT used for the top counter degrades as a function of the output charge squared as shown in this plot. So we want to keep the PMT QE within an acceptable level, that is a relative QE greater than 80% until we collect 50 mass advance data around 2031. So we need the two-check and beam gas background. The two-check beam gas background we expect increase with beam current squared. So this has to be kept, but this has to be kept constant by collimators, beam tuning, additional shieldings, and so on. So that means the top PMT hit rate could limit the luminosity in future. And we also concerned about the permanent damage on the vertex detectors by accidental huge beam loss. And we also found the synchrotron radiation from HR beam on illuminated on PXD sensor, as shown in this right bottom plot. So the synchrotron radiation from HR beam hit on the edge of the beam pipe of the straight detection, reflected back to the other side of the sensor, and creating this kind of particular specific pattern of the PXD hit rate distribution. So we should be carefully monitor not to irradiate PXD unnecessarily. So in 2020, as you know, we had a COVID-19 pandemic, but even under this situation, Super KKB and BEL2 was operated while minimizing risk of infection. So usually, before that, usually we had a operation scheme like as shown in the bottom diagram. So we had two on-site control room shifters to operate the detector, and one so-called BCG, BEL2 commissioning group shift, stationed on the accelerator control room, and who is an interface between the accelerator and the detector, and communicate with the accelerator people and control room shifters. But to minimize the person-to-person contact and avoid so-called 3C, closed space, crowded spaces, and closed contact settings, we decided to move one shell shifter from on-site to remote, and one BCG shifter from the accelerator control room to another building to reduce person-to-person contact. And we also had travel restrictions, and we had meetings, every meetings online. We also had some hygiene Then we managed the operation in 2020. So here we summarize the operation, accelerator operation since 2019. So the green dots show the luminosity, peak luminosity, and blue HER beam currents, brown LER beam currents, and the black points show the top counter PMT hit rate. So we squeezed the beta Y star step by step down to 1.0 millimeter in June. Then we achieved the world record of the luminosity, peak luminosity 2.4 times 10 to 34 square centimeter per second. Even at about a half beam current of the KKB at the KKB record. We also adapted the Club West scheme, firstly from LER and then HER. Finally, we achieved 0.8 millimeter beta Y star in the end of the last run. We also succeeded in keeping the top beam background level below the limit. As you can see, the level was nearly constant, though the luminosity was increasing. And in the next run in autumn, we try to squeeze beta Y star further down to 0.6 millimeter. And in the last run in 2020, we had a 56.7% of the machine time for the physics run. And our major concern issue was data taking efficiency that was only about 50% in 2019 autumn run. But we succeeded in improving it to 84% in 2020, thanks to less TAQ errors and more prompt recovery from the errors by experts' consistent effort, error analysis, and monitor by ELK software, and monitor more experienced shifters, and controlled injection better dead time. The last round, which was about, on average about 5%. This was a result of the injection background studies. So this plot shows the integrated luminosity per day in the blue bars, and the red line represents the integrated luminosity since 2019. And then the run ended on July 1st, and we accumulated 74 inverse femtobarn. And today in this conference, we can show the data accumulated up to mid of May, which corresponds to 34.6 inverse femtobarn on resonance and 3.2 inverse femtobarn of resonance data. So here we summarize the data analysis to be shown in this conference. And in terms of the performance assessment for the flavor physics program, we can show several things like the lifetime B flavor tagger and the so-called FEI, the full event reconstruction algorithm newly introduced in Bell 2, and so on. And we can also show some outset of flavor physics measurement, although we need more statistics for publication. That includes the branching ratio measurement, VUB, VCB, and branching ratio and CP asymmetry of charmless decays, and so on. Even with a
1 minute left.
Okay, smaller data set, we can publish some result in the dark sector, like Z prime to invisible. And this was the first of our physics paper, and axion-like particle search. This will be a second physics paper, just we submitted recently. And we expect this amount of data until March 2021, and we can have some prospect on the physics publication in the near future. also for physics, flavor physics, as well as a dark sector new particle search. And around 1 inverse out-of-band data before long shutdown in 2020, we can expect to surpass Bubble and Bell2 dataset. So I would emphasize here, Bell2 will join in with the hunting for new physics in earnest soon. So toward 15 inverse out-of-band, our ultimate goal of 15 inverse out-of-band data, here we show our projection, which was recently updated based on the past results of the beam operation. So in 2022, we will replace PXD detector to fill the currently missing the second layer. And after that, we try to squeeze the beta Y star down to 0.5 millimeter. And then recently we found that even further squeeze beta Y star down to 0.3 millimeter, we need an upgrade of the QCS, the final focusing magnet system. So we will have another long shutdown in 2026. Then we can expect to increase the peak luminosity above 6 times 10 to 35th. And then we expect to accumulate the 15 inverse out-of-band data in 2031. In summary, Bell2 plans to collect 15 inverse out-of-band data to extensively search for new physics in the flavor and the dark sectors, as well as to provide better understanding of the standard model and the hadron physics. The accelerator and the detector operation is in good shape. The world record of the peak luminosity 2.4 times 10 to 34 was achieved, while the TKB record was 2.1 times 10 to 34 with an acceptable beam background level. And we corrected 74 inverse Fermat band, and the first physics paper on dark sector was published, to be followed by other results on dark sector and flavor physics. And in a few years, we Bell2 will join in with the hunting for new physics in earnest. Thank you.
Thank you, Kodai. We have the time for a quick question. William. William, you have your hand raised.
I think I do. I didn't realize that my hand was raised.
Okay.
Maybe if I can ask, I would have a question. How the missing second pixel layer or significantly missing part of this second pixel layer is at the moment affecting the data taking, or would it be significantly better if it would be complete?
No, at this moment, at this event hit rate, we don't. The second layer. Without second layer, we can have a good performance, but at the higher occupancy, with a higher beam current or higher beam background level, we need a second layer to reduce occupancy and better vertex resolution.
So because you are waiting for the long shutdown for this, it looks like it is quite complicated to complete this this second layer. So you will measure another at least 1 year or maybe more with this being completed.
Right. So to reinstall the PXT, we need a complicated procedure, and we need around 10 months long shutdown.
Oh, okay. Okay. Thanks.
Okay, thank you, Kodai. Thank you for the questions also. And then we now move to the next talk, again from Bell2 by Slavomira Stevkova. If you want to share your slides, stage is yours.
Yeah, can you stop sharing the previous presentation, please?
Yes.
Thank you.
Okay.
Okay, so talking about the pixel detector, it is my very big pleasure to present on behalf of the Bell2 PXD collaboration, the performance and the background expectation of our detector at SuperCAGB. So the first talk that covered the pixel detector was already given by Felix Miller on Tuesday. And in his talk, he covered topics such as operational issues and beam losses. So in my presentation, I would like to concentrate on other topics, and along performance, I will concentrate on the backgrounds. Just a reminder, the PXD is the innermost detector in Bell 2. And as already discussed, currently we have installed fully the first layer and partially the second layer. So the importance of our detector has already been exploited actually in many analyses shown here at ICHEP, and in particular these are analyses that are sensitive to the parameters measured in the CP violation, but also the analyses that are measuring the lifetimes. In particular, I would like to highlight the result of the charm lifetime measurement, which you can see on the bottom left, where you can observe that the Bell 2 actually measures a factor 2 improvement in proper time resolution as compared to the previous B factories. And such an improvement is only possible thanks to an excellent performance of our detector. So in terms of the performance in the PXD, there are generally two metrics that we measure it with. So this is the vertex resolution and the hit efficiency. Thanks to the asymmetric and elliptical shape of the beam spot and very small size in Y, we can measure the resolution with horizontal tracks from the dimuon events. And you can see the resulting D0 distribution on the plot on the bottom right, where in the blue, you can see the distribution if it was only measured with a CDC and SVD, whereas in the red, you can see the distribution by adding the information from the PXD. And as you will observe, the improvement in the width of this distribution is nearly by a factor of 2 by adding the PXD into the game. I would like to also say that such an excellent resolution is also owned to very good alignment and tracking performance. What concerns the hit efficiency, which is defined as the number of tracks with an associated PXD cluster hit over the total number of sensor intercepting tracks, what we measure is an efficiency that is higher than 99% in regions without known defect, and it is actually very stable. Of course, one limiting aspect for our performance is the amount of the background that we observe in our pixel detector. And actually the limit is set with an occupancy of 3%. As I have already hinted, this is due to the fact that at actually occupancy of 3%, we observe degradation in vertexing performance because we increase significantly the probability to associate wrong hits to the track. Also at this occupancy of 3%, we start to observe a significant data loss if we want to take the data at 30 kilohertz trigger rate. Also, what is important to monitor for the PXD is the dose. So we expect to have a yearly dose of 20 kilogray in our first layer, given the conditions at the design luminosity. And until now, we have estimated that the dose that we have gotten is around 20 kilogray, but a more precise measurement is currently in progress. So the exact processes that contribute to the backgrounds are usually split into two categories. So first is the single beam backgrounds, which cover the following processes. So this is the Tushek scattering, which is scattering of the particles within the bunch, and therefore its rate is proportional to the number of particles times the density, and therefore have a sensitivity to the vertical size of the beam as well as the number of bunches. Then we have Coulomb or beam gas scattering, which is the scattering of the residual gas molecule in the beam pipe, and therefore the rate is proportional to the number of gas molecules times the number of particles, and therefore it has a dependence on the pressure and the effective C. Then we have the synchrotron radiation background, which is a consequence of the radial acceleration of the beam's particle achieved in quadruples and bending magnets. And finally, we have a background due to the continuous injection scheme, which is known as injection background. All of these single beam backgrounds have one thing in common. They can be mitigated with beam steering, collimators, and vacuum scrubbing. This is not the case for the second class of the background, which are the luminosity backgrounds, where the leading contribution comes from the two-photon process, which is shown here. So now that we have all these categories of background, we would like to study the composition of them at the PXT. And this is done by performing the following strategy. So in the single beam runs, we observe our occupancy and we decompose it into its component, taking the advantage of the different sensitivity to different beam parameters as shown on the, in the table at the top. Then in the luminosity, to measure the luminosity background, we take luminosity runs, and again, we observe the occupancy in the PXT, and we subtract the expected single beam component from it, and then the residual occupancy is assigned to the luminosity. So with this strategy in the mind, this is the situation of the composition of the backgrounds in our detector. It is also pictorially shown on the top right, where you can see the occupancy of the PXT as a function of time in a particular luminosity beam decay run. And you will observe that actually at the moment we are dominated by LER beam gas background. We also measure the data Monte Carlo agreement to see if our simulation can explain what we see, and this ranges between 0.5 to 5 depending on the component. In terms of the measurement of the luminosity background, which is also shown as a function of phi at the bottom right, what you will observe is that we have measured this luminosity background component, and also it is in excellent agreement with our analytical prediction. And finally, I would like to mention the fact that the injection and synchrotron radiation background are closely monitored, and what we see now is that the synchrotron radiation is dominated by the effects coming from HER injection. So using our current knowledge and the measured data Monte Carlo factors, what we can do is we can correct the design luminosity to see what will be the situation in the future. And this is what is shown on the plot on the bottom left, where you can see the occupancy as a function of PXD layer. And in future, we are expected to be actually dominated by the two-photon backgrounds as well as HER two-check. As you will observe in this extrapolation, we are missing the injection and synchrotron radiation background. However, I would like to assure you that for now, the synchrotron radiation has an acceptable contribution to the PXD. And moreover, as you can see on the plot on the bottom right, where you can see the PXD sensor heat maps in layer 1 in the phi Z plane, the synchrotron radiation is really located in only on 3 modules. In conclusion, with our current understanding, we predict that the occupancy that we should see at the design luminosity is below our occupancy limit. And I would like to conclude my talk actually with a toy simulation study of the impact of the PXD background on the delta T resolution. So the delta T, just to recap, is the difference in the decay time between the 2 beam mesons. And here what we have done is we have studied its resolution under 1 and 2 layer PXD configuration. And actually on the top right, you can see the scenario of evolution of our backgrounds as a function of the time within the next 2 years. And the different backgrounds are shown with a different color. And on the bottom, you can see the corresponding delta T resolution under the 1 and 2 layer PXD scenario. what you will observe is that the higher the background, we have the higher probability to assign wrong PXD hit to the track. And as you see in the green and blue color, only with one layer in place, we expect a significant performance degradation within the next 2 years. On the good side, this performance loss can be recovered by adding a second PXD layer, which is shown with this red and orange line. And on this topic, as already mentioned before, we plan to install our full 2-layer PXD in Bell 2 in 2022. So to conclude, I have shown you that a very good performance have already led to many physics analyses that are showing the results here at ICHEP. And to summarize the situation of the background, data Monte Carlo agreement is reasonably good. So far, we are dominated by a reducible LER beam gas background. And with our current knowledge, we expect that at the design optics, we should be below our limit. In the future, we are expected to be dominated by 2-check HER and 2-photon backgrounds. And we also closely monitor the synchrotron radiation and injection backgrounds. And finally, I have also shown you a toy performance study, which does exactly monitor the impact on the delta T resolution. And in this toy study, it shows actually the need for our full 2-layer detector. Thank you.
Thank you very much for the nice presentation. It was very clear. Are there questions? So in the meantime, just a quick question. I think you mentioned this, but I forgot. What's the distance of the first layer from the interaction point?
I think it's, I think I haven't mentioned it, but I think it's in tens of micrometers.
Okay, that was to understand how, okay, because maybe you can go back to one of the first slides. Mention the resolution, the difference in the pointing resolution when you add the pixels. Okay, this one. So I guess this gain you have because you are adding a layer which is closer to the beam. And so the effect is quite clear, yeah.
Yeah.
Okay, so I don't know if there are any other comments or questions. I don't see any raised hands. Thank you very much for your presentation, Slawomira, and I think you can stop sharing and we move to the next speaker, still from the Bell 2 experiment.
Thank you.
Thank you. It's Simon Bakker.
Yes, I'm now starting to share my screen. Do you see?
Oh yes, now we see, yes.
Okay, let me just move to the top. Okay, hello everybody, this is Szymon Bacher from Kraków, Poland speaking. I'll be talking on behalf of SVD group from Bell 2. Just let me start from a very brief outline of what I'll show you after a quick introduction about what the detector is and where it sits, and a little bit about some interesting technologies, some of them. I'll give you a short report on our operational experience, and then I'll tell a little bit about the performance. So since there was such a nice introduction by previous talks, I will not be going into details of how Bell 2 actually works and what it is. I'll just remind you of several important factors. So as you know, we have an asymmetric collider. So we clearly see the front and backward side because we have 4 and 7 GeV respectively for electrons and positrons. Also, we are very interested in having good observation for vertices because we are interested in B decays. So we want to be having our detector as close as possible to the interaction point. We also want to be able to withstand very high luminosities and integrated instantaneous. You already heard a little bit about that in previous talks, but I'd like to remind you about the accelerator talk by Onishi-san regarding that topic as well. So let's have a look on how we do the vertexing actually in Belle 2. It was already mentioned several times that we have pixel detector, which is the innermost part of our vertexing system, and I'm going to give you a little bit more information about silicon vertex detector, which is a strip detector that sits just above the pixel detector. So there are a few uses for that. One which is very interesting is that actually low PT tracks are sitting entirely within the SVD volume. So SVD has to be able to do identification for them. Also, we have to extrapolate the tracks to the PXD region so that the PXD knows which part of the detector to read out. We call that region of interest. And then we are also interested in being able to determine the K-short vertices. So how do we do that actually? I'm not going to give you all the technical details, but let me just point you to some of interesting features. As you can see, we have a slanted part, which is used for having better incident angle in the forward section. So forward meaning the direction that we have some remaining momentum after the collision. What we find very interesting, and that was a very nice challenge to do, we have what we call origami on-chip sensor design, which means that we have our front-end electronics sitting directly on the sensors, on the active part of the sensor, and we have very short cable length, so to say, the path length, electrical path length, thank you to what we call the origami, being the capton folded around the sensor with the electrical paths. And in total, we have 4 layers of those marvelous sensors. Those are double-sided silicon strip detectors. As you see, the slanted part, obviously it has to be trapezoidal shape, and we have larger and smaller sensors depending on where they sit to have best geometrical arrangement of what we have built. A little bit more about this on-chip sensor design. So we are using APV25 chips. I won't be going to all the details about them right now. Some of you might already know them because they were developed for CMS. And we put them directly on top of our sensors. And we have to cool them down somehow because one of the features of them is that each of them dissipates 0.4 watts, and we have almost 2,000 of them. So we have to dissipate the energy. So we have this very nice cooling system, which is another, in my opinion, very interesting technological challenge that we have covered. This is two-phase CO2 cooling that allows us to run at -20 degrees of Celsius. Now, all those things, they might not be so interesting at a first glance for a physicist, but they all contribute to us having very nice performance. Just before I show you the performance, a quick reminder in case if there would be some questions about that later on of our readout system. I've mentioned the front-end electronics being directly next to on top of the sensor. We feed out the cables, which is copper twisted pair cables, to our junction boards sitting just outside of the active volume, and then we feed out with the cables to FPGA systems sitting on top of the detectors in racks to make the proper digitization and all the other work that's going to be done there. So let's have a look on how this was all put together. This was fairly large challenge to do. The first beam test beams were performed still in 2004, which was not the final sensor, but it was already investigating in direction of what we want to have. And then in May 2015, there were some first tests done with complete ladder. And then, jumping quickly through the time, even though it was a lot of work, in 2019, first half shelves of our detector were built and then later on merged with PXD, and soon later, still in 2019, installed in our detector. And we are running since March 2019, and we are very satisfied with how it goes. Let me just try to convince you that we are actually having good reasons to be satisfied. So let's start from stability on slide number 9. You've already heard about diamonds that we use to investigate the doses that we are having. And so we were very interested to see how we perform in time and in dose, if our parameters are within our expectations. So the main part is that noise and leakage currents are within expectations, and the way how they develop in time and develop in function of integrated dose is also within expectations. You can see from that plot that even though dose which is being accumulated is rising all the time, our noise is flattening out slowly, and this is as we expect. We also don't see in SVD, we don't see any damages that would hinder the performance. We see that there are radiation effects, but we don't see the damages that would affect the performance. And just a nice show off, we have very nice and stable efficiency, averaging well above 99%. So let's have a look on cluster energy. So and the histograms of how much energy is deposited for each and every track passing through. They are very well within what we were expecting. So as you see, we have this structure which is having asymmetrical beams. So we have different incident angles depending on which sensors we are looking at. So here we have cluster energy histograms for layer 4. And since most of the particles are traveling in the forward direction, you can see that we have different histograms for them. They are also showing a difference between U and D site, which comes from the fact that those two sides have different pitch between the strips that we are having. Also, let's have a closer look on our heat efficiency. As I've mentioned, we have heat efficiency well above 99%. Actually, you can see that broken down into layers and even the very precise map. By the way, if you would be looking at the map, the ladder number corresponds to phi angle, whether within those groups corresponds to layers, and within the group you have the larger Z when you go up. So we don't see any radiation effects on efficiency. Efficiency seems to be very stable in time. And just if you look at the map and you will see some sensors having lower efficiency, this actually comes from the production defects. Those sensors just have production defects, which were known upon installation already. So let's also have a look on the signal to noise ratio. So again, this is very well within our expectations. We have 13 to 33 signal to noise ratio. Again, we see the difference depending on the incident angle as well as depending on the U and V site. So let's also progress to our spatial resolution, which I believe is one of very interesting features of our detector. Now, contrary to what Sławomira was mentioning, we don't look here at the beam spot size. Instead, we look at the resolution of the detector itself. So it's slightly different measurement. But we also use time nuance here in this investigation, and we actually use on unbiased tracks. So what comes out with our present algorithms is 20 micrometers, which we are already happy with, but we also see the room for improvements that are being worked on right now. So let's also have a quick look on the time resolution. This is not something that is usually mentioned when you look at this type of detectors. I mean, this is mentioned, but not one of the show-off points. But we are very happy to have, with our present chosen operation mode, 2.35 nanoseconds time resolution. Now, this can be very useful if you look at occupancy and data quality when you're trying to reconstruct. I'm showing you here the histogram of times, and you can see two lines, blue and red. And blue is for all clusters we see. So what's the time for all the clusters we see on the sensor, whereas red is for those clusters that are having some tracks associated. So you can see that for those without the track associated, you see some structure in the negative times, and this comes from the previous event. So this would be associated to the track from the previous event. The more events you are having, the more often they come, the more likely you are to have some previous events leaking into new event you are trying to analyze. And now what we are investigating now to use our marvelous time resolution is to reject those off-time hits. Actually, I should mention to you that we are right now using 6 data samples per one strip per one event. We are investigating other options as well, as we have some room for configuration here. And those 6 samples right now are having interval of 31 nanoseconds. And analyzing those samples gives us 2.35 nanoseconds. Yes, so let me just quickly summarize. I mean, there were years of intense work and developing quite a few new technologies and tackling several challenges. And it gave us a very nice detector, which is running smoothly since 1.5 years. We don't have any major problems with our detector at all. And we already have achieved very nice resolution of 20 micrometers for spatial resolution and 2.35 nanoseconds of time resolution. We are very happy with our efficiency, which is well above 99%, but we still see room for improvement in how our software analyzes the data. So stay tuned for future conferences where we'll be showing off hopefully even nicer numbers. Thank you.
Thank you, Simon. So we have some time for questions. Raise your hand if you're interested.
Sorry, I would have maybe a question. Maybe you mentioned probably, but is it a digital or analog readout?
Well, let me just go back to the slide about how we do the readout. Yes, here we are. So our sensor is connected to APV chips that are converting analog signals to time. And then we feed that to, and then we feed that to FADC, which is doing the real digitalization for our sensors later on.
Okay, so you are reading out the full waveform?
We are reading out the waveform, yes. We are reading out six samples from the waveform. We are also investigating reading different number of samples from the waveform, but right now it's 6.
Okay, and what is like, how to call it, the charge, a medium charge that you are reading out for the MIP?
I don't remember it offhand, off top of my head. So if you could please come back to me with that question and offline, I'll provide you with informed answer.
Okay, something like a 3.5 femtocoulomb or something like this.
I might try to have a look on my notes because I don't remember that really. But
okay,
I think it would be much more realistic if I tell you offline.
Okay, thanks. Because you have 300 micrometers thickness.
Let me get back to the thicknesses. We have the slide on that here. So the thickness of the detector itself, yes, is 220 micrometers.
Oh, okay, and this is fully depleted, I would expect.
I believe so, yes.
Okay, thanks. Then I would expect something around 3.5, something like maybe 4 femtocoulombs. Okay, thank you.
Thank you.
Okay, thank you. So we have to move to the next speaker. We thank Simon again.
Thank you very much.
And we move now to Ina Carli from the Chinese Academy of Science, who is going to talk us about the silicon strip tracking with the LHCb in the future.
Hello. Yeah, thank you. Can you see the slides?
Yes, we do.
Yes. Okay. So thank you very much for the introduction. Now, between all the Bell 2, I will jump back to CERN and to the LHCb silicon strip tracking detector. We call it Upstream Tracker. So I'll present the current status and what we are building. So the LHCb detector at the LHC is a single arm forward spectrometer. It's mostly focused on the precision, beauty and charm physics, but we are also extending other interesting analysis, so QCD, direct searches for new particles, fixed target physics, and so on. During the previous LHC runs, we collected about 9 inverse femtobarn of dataset. However, as you would see from some of the presentations from the LHCb, a lot of our measurements are statistically limited. That's why we decided to do a large upgrade and a lot of changes to try to collect larger data sets and also cleaner data sets with a higher amount of the interesting rare decays. So for the upgrade from LHC, we are going to request higher instantaneous luminosity. The LHCb is usually running so-called at the constant luminosity, so we will have much higher, it will be about 5 visible collisions per bunch crossing. We are completely changing all electronics in the whole detector, and it will allow us to read out at full collision frequency, so that's 40 megahertz. And we are also changing the trigger to software only. So we will be able to take all the data and then have time to process them with high quality trigger, very similar to the online selection, to the offline selection and to the analysis. For detector, we are completely changing all tracking detectors. I will be speaking about the UT, so that's the tracker before magnet, but also my colleagues already on Tuesday, you heard talk about Velo and about sci-fi, that's the tracker after magnet. And also this morning you heard about other upgrades, for example, reach and some small other changes of the detector. So what's the role of the UT? As I already mentioned, it's the tracker before magnet. So this greatly improves the PT resolution if we would compare to the tracking which would use only Velo and the sci-fi after magnet. And also we can suppress the ghost tracks. The upgrade aim is to try to do all this while keeping the efficiency and also to ideally speed up trigger and do other stuff. So the trigger speed up comes mostly from the fact that we can, while matching the segments on the trigger, we can use the UT hits. For example, if we take tracks which are from Velo to UT, we can remove the very low PT tracks and we are able to then go on tracking through the magnetic field much less tracks. So this significantly speeds up the trigger. Also, we can make the search window in the sci-fi tightened. So you see here on few plots the performance. So in blue is tracking without the UT, in green is with the UT. So you see the efficiency more or less when we require the hits in UT stay about the same, but the number of ghost tracks is significantly improved. In orange is the number of expected collisions already. I mentioned 5 collisions per bunch crossing. So now how to build such a detector? It's going to be constructed from 4 detector planes. Each of them is about 2 square meters. 2 of them, the first and last, have vertical strips, and 2 will be rotated by plus and minus 5 degrees. So sometimes we call it X, UV, and X. This comes from simulations from trying to have a good enough resolution, but also from the occupancy. On the UT, we have finer granularity than on the previous detector, TT, and also we are closer to the beam pipe, so we increase the tracking coverage. So the sensors, already mentioned that it's silicon strip sensors. Most of the sensors, what we call is type A, so that's the ones in green. These are standard strip sensor from Hamamatsu, pin and 320 micron, and the sensors are about 10 by 10 centimeters. For the inner regions, as there is much higher track coverage, we need something which has finer segmentation, but also which is more radiation hard. So we selected sensors which are NMP, they're a bit thinner. And then in pink, there are also sensors which have half length. So this will help us with the occupancy. And also, as you see, we need to have a circular cutout around the beam pipe to be able to come much closer to the beam. Some of the features which are not usual for other detectors, you see on this slide. So we have for the A type sensors, which have larger pitch, we have embedded pitch adapters. We also have top side high voltage biasing because our sensors, as you will see, are glued on a support stave, and we have cutouts around the beam pipe. All these features were tested on the test beam. You see some of the results. These are for minis, and it's signal to noise ratio for various configuration. So you see that also the different colors are unirradiated nominal dose or the 2 times expected dose. So you see that the signal to noise ratio is very good, and we don't see basically much difference if we do top side or back side biasing. So these work very well. To read out the signals, we are going to use a custom developed chip. We call it SALT. So this is 128 channels of 6-bit ADC. As we have both PNN and NMP sensors, we are going to be able to read out both positive and negative pulses. So we have polarity is one of the bits of the data we take. And in total, there will be nearly 4,200 chips. Some example of what the chip does. So we have per channel trim and a pedestal correction. So here you see an example of the data. As how to read it, it's per one chip. So the x-axis is the number of strip or number of channel, and the ADC value is on y-axis. So you see the raw data and then after the baseline correction. The chips are able to do command mode noise correction over the whole chip. We also are planning to use zero separation of about maybe value in between 2 and 4 ADC units. So then we will have a rather low amount of data to read out. Then from the sensors and chips, we are going to build modules. Here you see one of the first modules constructed. So we are using a hybrid circuit with 4 or 8 chips, depending on the number of strips. And we put it on a stiffener or a support structure, which is under. You see just the white tabs from it. Here, the hybrid and sensor are thermally decoupled. There is about 1 millimeter gap in between to try not to heat up the sensors. In total, there are 968 modules, and these modules will be on support structures we call staves, 68 staves. So stave is a low mass support structure, basically from which that's the basic components we build the detector from. It has integrated titanium pipe, which is running right under the group of chips. And this is to use the CO2 cooling. It has also glued Kapton tape for readout, powering, and grounding of the modules. And we are, the overlap of sensors is in such a way that they completely cover. So there's sensors on both sides, and they're interleaved. So here you see some of the designs, and on the next slide, you see some of the first production components, how they look like. To read out these detectors, we decided to put readout electronics quite close, so just above and under the staves. We will have data control boards. You will see in a while in the CATE. So these boards are holding few chips, which are used for data formatting, timing distribution controls, and other functions. And we are using the GBT's chipset developed by CERN. So you see here one of the boards, which has 7 GBTX chips and 1 SCA chip, that's the black chip, which is used for slow communication and controls of the readout chips on the detector. Each of these boards is then using 4 transceivers. You see on the left, that's the versatile link transceivers. So in total, there are 8 optic fibers to read out this card. 6 of them are for readout of data, and 2 are bidirectional for controls and for trigger and for timing. So then these cards come in what we call PEPI crate. So there will be nearly 250 boards above and under the staves. So here you would imagine at the bottom there are staves. Then in blue, there are flex cables, which bring the signals to this big crate. And then we have the data control boards to power the staves and to read out. Then we are directly getting the signals out with optic fibers and to the surface computing center. What we did already in the previous, this year and last year, we performed a lot of system tests. So here on the picture, you see, for example, a stave with 7 production quality modules here on the front face. So this is using final version of powering and readout schemes to be able to validate them. We also have a cooling power plant, so we tested the components in a wide range of temperatures. We check the performance, long-term stability, and other properties. So we are quite sure by now that the detector works very well. Also, this setup allows us to do software development, to test the mounting procedures, and to try to debug the last few surprising things if we find any. Some performance from the stave. What we found and what we measure is that the noise is very similar to the single module tests, which proves that our powering and grounding schemas are well designed. And you see an example here of the noise measurement. This is for a sensor which is at 400 volt bias. The depletion voltage is usually around 200 volts. So this is well depleted at 5 degrees Celsius. It's a bit warmer. We will be running around -5 degrees. And you see that the measured noise is around 0.88 ADC counts. We know that the MIP signal, or when we do injection, is about 13 counts. So signal to noise ratio is about 15. And you see with the channel ID, very nice flat distribution of the noise. What we are going and what we are working on since a while, and this year, there is a lot of work with integration. So when we have these nearly 70 staves, they need the box, they need cooling pipes, support structures, alignment, and so on. So all this is being designed and finalized. And around the box, because UT needs to be open because of the breakout of pre-pipe, or maybe for fixes during shutdowns, we need to have the box in 2 halves, and we need to have flexible cable chain and all the powering, all the cables, and so on. So all this is prepared and being worked at. So what's the current status of the project? As other labs, all our production sites were impacted by the lockdown, some of them longer, some of them sooner, some of them later. But we are slowly coming back, and the module and state production is ramping up again. All the mechanics, cabling, cooling, and other stuff are being prepared at CERN. So this is on track, and we are aiming for installation underground in the LHCb cavern before fall next year. So just for the LHC startup, hopefully. So that's the status. Thank you for your attention, and I'm waiting for questions.
Thank you, Ina, for the very nice presentation. So maybe to start the discussion, I have a few questions on your slide 11, where you describe the assembly of the detector with all the other components. So what's the thickness of these Kapton flexes that you are using?
This is difficult. I don't have exact numbers, but if I remember well, it's maybe 300-400 microns, but of that, the copper is around 100 microns. I can check exactly the design document and also.
It's copper. Okay, next question.
The lines are copper, and we did a development with one German company, or well, started with a few companies. So this is made flexes for us. I can send you the details.
Okay, thank you. Yes, I'm really interested.
Yeah, this was difficult to design.
I understand, because we had similar issues with this. And also about the support material, you mentioned low mass. Is it carbon fiber?
Yes, it's honeycomb.
It's honeycomb.
Okay. Yeah. Okay. Then at the end of the stave, it's not visible here, but there is some, I think, epoxy structure to kind of support it more.
Okay. Thank you. Are there any other questions to Ina?
Yeah, maybe I would like to ask, what is the reason why you are mainly using P in N over N in P? just the price, or is there some other?
Yes, it was for price, and because the radiation damage is not so much in the LHCb is very ununiform, so it's the highest in the middle. Then the green sensors, they will see around 10 to 13 maybe over their lifetime. So.
Okay, one thing is of course radiation damage, but also the speed of the signal. So you are fine with the, let's say, slower signal.
Yes, it's going to be, so it's ADC, but we are going to sample the signal. So if we have it well timed, what we care about is the over spill to the next bunch crossing, and that is very low. So the chip is rather fast.
So you have, I expect you have digital readout with some threshold.
No, so it's more complicated. We are going to read out the ADC value, but at the given time in the bunch crossing.
Oh, okay. Okay, thanks.
And this is going to be zero suppressed, but for tests we are able to run also non-zero suppressed. So I have actually in backup, it's a bit complicated. If you see on slide 22, it's some pulse shapes, but these are pulse shapes of all the strips and on one chip, so it's 128 strips, and you see the one signal. But this we take by literally scanning, so you change offset and you always read out the ADC value.
Okay, thank you.
Okay, thank you. I think we need now to move to the next speaker.
Yeah, thank you.
Thank you,
for
Ina.
Questions.
Thank you very much. So we move to William Sutcliffe, who's gonna talk us again about Bell2 status and future development of the full event interpretation algorithm. So we move to software.
Can you see the slides okay?
Yes, can you make this full screen?
So I made it full screen. So does it not show full screen or?
No, not yet. It's clearly visible, but if you manage.
Does that work or?
Well, to me it seems always the same.
I also had the problem with Ocular in presentation mode.
Maybe I just quickly try.
Are you sharing the application or the full screen? Because if you have a Mac and you're sharing the application, it doesn't work sometimes.
I don't have a Mac. Yes. Can you see now or?
Now we just see you. We don't see any slides anymore.
Sure.
But anyway, it was clear. So even if, okay, let's see now. Try either one of those.
No, this is not the presentation mode. Does it work now?
Yeah, perfectly. Okay.
Okay.
Yeah,
okay. So hopefully that works now. Okay, so today, good afternoon, everybody. Today I'm going to be presenting full event interpretation, which is the Bell2 tag-side reconstruction algorithm. So firstly, why do we need this algorithm? Well, it turns out that a lot of interesting physics can be obtained by measuring several challenging decay modes involving missing neutrinos. We see an example of this here on the left, where we have this decay B to lepton neutrinos. So you only have one track from the associated lepton to reconstruct this state. Or even more challenging here on the right, we've got B to nu bar, so you have no particles to reconstruct this with. So we're effectively in this situation where we're blindfolded, and we'll see that full event interpretation really gives us a fighting chance to measure these modes. So now I just want to quickly introduce the concept of tag-side reconstruction. And what we're really doing here is exploiting our unique event topology in which we collide an electron with its antiparticle, the positron, to produce upsilon for S particles. Over 96% of the time, these decay onto B plus B minus or B naught bar. So in tag-side reconstruction, we reconstruct one of the B mesons in certain decay modes, so either hadronically or semi-leptonically. So hadronic is shown here. Now one can study the remaining B in the event decaying to a given signal side. So here's the signal side we saw earlier, being a lepton and neutrino. By reconstructing the tag side, we've gained important constraints. For instance, here, the knowledge that we had a B plus tag implies that we have a B minus tag on the signal side. Also, we have the tag side formentum, which combined with our E plus E minus formentum allows us basically to derive the neutrino formentum with this equation here. So now I just want to introduce the actual algorithm. So what the algorithm does is it employs over 200 BDTs, each charged with the task of identifying or classifying particle decays that occur in B meson decay chains. And in doing so, it's able to reconstruct over 10,000 unique decay chains of B mesons. Here you see the hierarchy of the algorithm. So the algorithm actually starts from tracks and clusters in the event, assigning these to final state particles like electrons, pions, and photons, each with their own dedicated classifiers. Then it goes through several stages of reconstructing intermediate particles like J size, K shorts, D mesons, each again with classifiers for each decay mode. Finally, the algorithm goes on to reconstructing around 80 decay modes of B plus and B naught mesons, again with their own dedicated classifiers. On the right here, you actually see the beam-constrained mass distribution of the B plus tag sides and B naught tag sides below in early data. And you see different categories of decay modes. What you see here is actually that there's the dominating modes are really D pi, D star pi, DN pi, and D star N pi. But there are several other categories. And actually recently, modes with baryons were added into this hierarchy. So with protons and lambda Cs in their final states, and you see the contribution in light green here. So now I want to talk a bit about the role of the tag side classifier. So what this actually does is discriminate between correctly reconstructed tag sides from incorrectly reconstructed tag sides or background from E plus E minus to QQ bar, which we name continuum. In this plot below, you see a comparison of the shape of this classified distribution between simulation and data. And what you see is to the far right, at a classified value of 1, which in the log of this variable is 0, we get a peak from correctly reconstructed tag sides. By cutting on this variable, so here I show two selections, a looser selection and a tighter selection. And on the right, I show the corresponding beam-constrained mass distributions. And what you see is by cutting tighter on this variable, you're actually able to remove a large amount of background, increasing your purity. But obviously, you do suffer some loss in efficiency. One thing I also want to mention at this stage is quite a big caveat of the algorithm is that the efficiency of the algorithm differs significantly between simulation and data due to its complexity. As a result of this, the algorithm requires a careful calibration. So this can be done by measuring a well-known signal side. So we've already done this actually using B to XL nu decays given their large branching fraction of 20%. The topology for this selection can be seen here in the diagram below. So we start by reconstructing a tag side, and here we've only done this hadronically. We require the beam-constrained mass distribution to be above, to have a value above 5.27 GeV. We also cut on the tag side classifier, but we actually have several choices of cuts and derive calibration factors for each. For the signal side, we select an lepton using our lepton identification information. We require that the momentum of the lepton is greater than 1 GeV in the B rest frame. The calibration factor itself is defined here. So what we're doing is taking the amount of XL nu decays observed in data, normalized to what is expected from simulation. We determine the number that we observe in data by fitting the PL star distribution. So here you see fits to this distribution for B plus E minus, B plus mu minus, and the corresponding channels for B naught mesons below. In these fits, you can see background from E plus E minus to QQ bar in red. We've got background in orange, where the electron could be either fake or from the secondary decay of D meson, and all the other components are contributing to XL nu. Here we're including DL nu, D star L nu, D star states, and other XCL nu states, and also XUL nu. The reason we can include actually XUL nu in this fit is you can see here, because if you go high in PL star, the kinematic endpoint of XUL nu is actually slightly higher than XCL nu. And it's very nice, and already in our data, we can see a contribution in data from XUL nu decays using our tagging. So here I summarize our results for the calibration factors. So here, for instance, for this channel B plus E minus, you can see the calibration factors for the different choices of cuts on the classifier output. You can also compare the electron channel to the muon channel, and the results are consistent within uncertainties. And here you can just see the average. On the right here, you see the corresponding results for the B0 case. So here I've just summarized actually the actual calibration results for B plus and B0. In the table below, you see the sources of uncertainty and percentage for the loose classifier cut choice for the various channels. And just to flag up here, the dominating systematic uncertainty at the moment, it comes from the freedom of PDFs in the PL star fit. So we have some shape freedom for those PDFs, and this is around 3%. The next leading systematic is from the branching fractions of B0 and B plus, the XL nu decays, which is around 2.1%. And then for muons, we have an uncertainty of around 2.1% from lepton ID. Here below, you can see the impact actually of applying the calibration factors. So what we show is the efficiency of the algorithm as determined in simulation, but corrected for by the calibration factors. And we plot this against purity. So each of the 3 cut choices correspond to one of these points, going from a looser cut, which is lower purity, but a higher efficiency, to a higher purity when you cut tighter on the classifier, but a lower efficiency. And you see this trade-off for B plus in blue and B0 below. Now I want to talk about some of the first analyses searching for signal sides with this tag side reconstruction algorithm. So what we've looked at is beta pi L nu. Here is a signal side, and also shown here below, beta D star L nu, where the D star decays with a charged slow pion, a D0, and the D0 goes to K pion. In both of these cases, we can derive a missing mass squared variable, which is actually just the square of the neutrino momentum we introduced earlier. And here on the right, you can actually see the comparison between data and simulation for this missing mass squared variable for beta pi L nu above and beta D star L nu below. And here, I should note the calibration factors are implied, and we see quite a good agreement between data and Monte Carlo. One can go a step further and actually fit these distributions, and in doing so, one is able to measure the branching fractions for these 2 modes. So you see the beta pi L nu branching fraction and beta D star L nu branching fractions. These are consistent with world averages, but right now we do have quite large uncertainties. One thing I should note, it's very amazing that already in such a small amount of data, we can observe a mode like beta pi L nu, which is actually quite rare. And we observe this with 6 sigma significance. Also, you can see that these samples are very pure because of the fact that we use tagging, especially this D star L nu peak, and we get a very nice resolution already. So going forward to the future, there's a number of developments in the pipeline. So one of these is that we've actually successfully applied the algorithm already to the upsilon 5s resonance, where one produces BS mesons. And this has been done using the Bell legacy dataset, but hopefully Bell 2 will also have an upsilon 5s dataset in the near future. We're also exploring deep learning extensions of the algorithm. So here you can imagine feeding in all information from tracks and clusters in the event, such as kinematics and particle identification, going through several hidden layers in order to predict something like the flavors of your B meson, and the foremental. We've also explored more exotic architectures like graph networks, given that they naturally suit particle decays, where particles can be labeled as nodes and mother-daughter relationships are edges in the graph. Going forward to thinking about the full event interpretation in the near future, we can really look forward to the exciting physics results to come from the growing number of BTAGs. This can really be illustrated here by looking in 2018 when we had 0.5 femtobarns of data and we had around 400 charged BTAGs observed peaking in MBC. And going forward to now at a similar level of purity with 35 femtobarn, we're seeing around 85,000. And hopefully this number will grow soon. So in conclusion, the full event interpretation is performing well in early Bell 2 data. A first calibration of the algorithm was performed with beta XL new decays, and you can see for a loose tag side classifier selection, the calibration factors for B+ and B naught. The decays beta pi L nu and beta D star of nu have been rediscovered with the algorithm and their branching fractions measured. And at the moment, we're exploring several deep learning extensions of the current algorithm, and we're looking forward to more physics with tagging to come soon.
Thank you very much, William, for the nice presentation. Indeed, really complex, this algorithm. It must have taken a lot of time to get to the results. I don't know if there are other questions. Maybe I have one about the training of your algorithm. Are you training on simulations only or on data as well?
Yeah, so the training is entirely on simulation, and that's in part why we have to have this calibration, why it's so essential, because we have so many classifiers that essentially you're bound to get mismatches, because you can imagine all the different features that go in there. There's going to be differences in data and simulation. And yeah, the training process is also, as you say, it's quite complicated. Generally takes around 5 days running on 2,000 nodes. So
I can imagine, yeah.
We produce essentially all the training data sets for these different sub-modes and train them all.
Okay, thank you. So if there are no other questions, we thank you again. Thank you very much. And we move to the next speaker. Again, from Bell 2, we have Laura Zani, who is going to talk us about track reconstruction efficiency using E+, E- events.
Hello, everybody. Can you confirm you can see my slides and hear me well?
Yes,
okay.
We see and we can hear you.
Okay, perfect. So, hello, this is Laura Zani from Marseille on behalf of the Bell 2 collaboration. And in this presentation, I would like to talk about the track reconstruction efficiency measurement, which exploits the E+ and - annihilation into tau pairs at Bell 2. So briefly, this is the outline of my talk. I will first give you the motivation for this kind of measurement and introduce you the experimental context before going to the details of the analysis strategy. And I will explain how we select the event and suppress the background, how this compares to simulation, and the calibration procedure we devised before giving you the results. So let me start here with this statement that the track reconstruction efficiency for Bell 2 physics is a real key performance driver. And the reason is simple. It's because our real detector is different from what we simulated. So the goal here is to measure the track reconstruction efficiency on both data and simulation and quantify the discrepancy, this delta star here. And based on this measurement, we want to assess the systematic uncertainty which we have to assign in every physics analysis related to the track performance. So the key quantity we are going to measure here is this discrepancy, delta star, which is defined as 1 minus the ratio of the efficiency on data and on simulation. And before going on, let me very briefly recap about Bell 2 physics. We have heard already in this session, so let me just say that Bell 2 belongs to the B factory families, which are dedicated experimented E+ and - asymmetric energy colliders, whose center of mass energy is tuned at the upsilon 4s 10.58 GeV. which mainly decays into BB bar pairs, but actually at the same center of mass energy, we also have comparable production cross-section for CC bar and tau pairs. So the advantage here with respect to Hadron Collider are many. First of all, let me mention that we can build a hermetic detector with excellent bit capability, and especially the possibility to have high efficiency for neutral reconstruction and to close the kinematic of an event, and therefore dealing with missing energy final states. So the future of B factory now belongs to the Super KEK-B Collider, which is the major upgrade of KEK-B, as we have already heard in the previous talks. So it's installed at KEK laboratory in Tsukuba, Japan, and it will provide the world highest luminosity by applying the large crossing angle nanobeam scheme technique, which is sketched here in this drawing. So the goal is to squeeze the vertical sides of the beam at the interaction point by reducing of a factor of 20, what is called the vertical beta function, this beta y star. And at the same time, we will double the beam currents. So these two parameters, as you can see from the bottom left formula, are the main handles to increase luminosity. And Super KEK-B will reach 30 times the KEK-B peak luminosity, which means 6 times 10 to the 35 per centimeter square per second. And I think this plot has already been shown today, this session. So this is the breaking news from last June 24th, when we overthrew the world luminosity record. We reached 2.4 times 10 to the 44 per centimeter square per second of instantaneous luminosity. So let me come back now to the Bell-2 detector. Here's a sketch of our detector, which has a cylindrical symmetry around the interaction point where it is installed at Bell-2 at Super KEK-B Collider. And it partially reuses parts of the Bell detector, but it has been upgraded to cope with higher backgrounds and ensuring at the same time excellent performances. So from the inside to the outside, we have a completely new vertex detector, which is based on 2 layers of silicon pixel detectors. Only one fully installed, the second one is going to be finalized next year. And then 4 layers of silicon strip detectors. And together with the central drift chamber, the CDC, they provide the tracking volume for the Bell-2 detector. Then we have devices which exploit the principle of Cherenkov light detection in the barrel and end cap region for particle identification. And then for the identification of electrons, photons, and neutrons, we use the electromagnetic calorimeter, this ECL. And outside the return yoke for the superconducting magnet, we have the outermost subdetector, the K-long and muon detector. As you can see from the left plot here, from the integrated luminosity curves. So in red is shown the total integrated luminosity, which we collected since the beginning of phase 3, last March 2019. And now we achieved more than 74 inverse femtobarn of data, with the final goal at the end of phase 3 to collect 50 times the data set that was collected by Bell, which means 50 inverse optobarn of data. And now let me come back to the strategy for this measurement. So the idea is to exploit a tag and probe method, which targets the E plus E minus annihilation in the tau pair, where one tau decays leptonically and the other one decays hadronically to 3 charged pions. So according to the geometry of the charge tracks in the final state, as you can see from this drawing, we refer to this event as the 3 by 1 prong event, since we have 3 charges in one hemisphere and just 1 charge tracks in the opposite one. The idea is to reconstruct these events by tagging just 3 out of 4 tracks that we expect in the final state with a total charge equal to plus minus 1. And then, because of charge conservation, the 4th track, which is our probe in blue here in the drawing, has to be there. So we count the number of events where the 4th track is found, and they belong to the N4 category. And the events where we cannot find the probe track, we assign them to the N3 category. And then we compute the track reconstruction efficiency convoluted with the acceptance of our detector as the ratio of the event where the 4th track is found, N4, to the total number of reconstructed events. For this measurement, we exploited the full 2019 datasets, which means an integrated luminosity of 8.8 inverse femtobarn, and the equivalent of 100 inverse femtobarn of Monte Carlo simulation officially produced. And for the signal sample, we simulated tau pairs event for backgrounds, mainly plus and minus annihilation into QQ bar pairs, and low multiplicity events, which means radiative lepton and 4 lepton final states. And let me remark here that despite this is a low multiplicity event, actually it's really boosted in our detector, and it deals with high density of tracks, so it's quite challenging for the tracking. And also it allows to investigate a wide medium momentum range between 0.2 and 3.5 GeV/c. And again, if we consider the production cross-section for tau pairs at ε4s, which is almost 1 nanobar, and we multiply by the useful branching fraction to obtain the desired topology, and for the integrated luminosity available from 2019 data, we end up with quite a large statistics for this measurement, so more than 1.2 million events. And let's see how we select the event here. So first of all, we require on data that ECL triggers are fired, and we do not use any trigger fired by the tracking devices in order not to bias our measurement. Then we define our track selection thanks to 4 different track lists, which all start from the good quality tracks which are coming from the interaction point. Then on the loose spinal list, where we look for the probe, we do not apply any further selection not to bias the measurement of the efficiency. Instead, we tighten the selection on the other track list, and specifically we define the tight pions list, which is a subset of the loose pions. And then on the leptonic track in the opposite hemisphere, we apply particle identification selection to distinguish between the muon and electron channel, which are made orthogonal thanks to this selection. And the event is finally selected by constraining the number of candidates per each track, but not the total track in the event, in order not to lose statistic. Again, we can have also 2 different charges for our samples according to the relative sign of the charge of the tag pions here. We can have opposite sign samples and same sign samples. And now let's see how we suppress the background. So first of all, we exploit our topology, and we require an angular isolation for each of the tag in the 3-prong hemisphere to be larger than 120 degrees with respect to the 1-prong track in the opposite hemisphere. And also we require a good results of the fit to the vertex of the 2 tag pions here displayed in yellow. And then we reject the radiative QED contamination and also the continuum QQ bar background by requiring that the transverse momentum of the 1-prong track is within 20 and 80% of the beam energy. And also we require a minimum opening angle between the 2 tag pions in order to reject relative BABA events, which are much more jet-like and squeezed. And we constrain the number of neutral pions and photons in the event. Finally, the last selection is applied to the invariant mass of the 3 tag tracks candidates. And also, since we observe some contamination from 2 photons events which are not simulated in our Monte Carlo samples, we devise a specific data-driven veto for the electron channel, just for opposite sign charges, since these kind of events can mimic our signal topology when one of the 2 electrons in the final state is out of acceptance and the virtual photon here decays to a lepton pair. So let me show you now the comparison between data, black dots in these plots, and simulation represented by the color stack histograms, which is scaled to data luminosity 8.8 inverse femtobarn and weighted bin by bin for the measured trigger efficiency on data. And for more details about this measurement, you have some information in the backup, but you can also have a look at yesterday's talk from Peter Rados. And you can see in the lower panels here that our agreement is very nice and the data to Monte Carlo ratio is consistently within uncertainty peaking at 1. So before giving you the results, let me mention our calibration procedure to calibrate the estimator of our discrepancy to represent the true value of the difference we want to measure. So we fully exploit our simulation here, and we modify the signal samples, so the tau pair event samples, by introducing a known per track inefficiency. And we do this for different inefficiency points. Then we apply exactly the same analysis chain, and we reconstructed the discrepancy with our estimator, this delta measured, plotted on the y-axis, as a function of the known artificial inefficiency which is introduced in the Monte Carlo sample. And by fitting the slope of these curves, we extract this calibration k-factor that are shown here in this top right box, are used for calibrating the discrepancy estimator. And now let me show you the results. So what is shown in these plots, respectively on the left as a function of the one-prong transverse momentum and on the right as a function of its azimuthal angle, are the track reconstruction efficiency convoluted with the detector acceptance, in blue for data and in orange for the simulation. And data yields have been subtracted by the remaining background, which is estimated from simulation. And again, this estimator plotted on the y-axis comes from the ratio we defined previously. And in the lower panels, you have the distribution for the calibrated discrepancy as a function of these two kinematic variables. So now let me summarize the results for the calibrated discrepancy, which are plotted here in this plot on the right. So you have the discrepancy measured for different channels and charge samples for different data taking periods of 2019 data set. And finally, the last 4 entries of this plot show you the combined results on all the samples, charges, and on all data set periods. And here the systematic uncertainties are taken into account, and the dominating contribution comes from the charge dependence. And this is expected to be largely improved when we will measure the charge asymmetry effect on the tracking performance. So this is a measurement that we already plan to do, and we expect to further reduce the systematic uncertainty, which is now dominated by this effect. So here you have the final results for the overall calibrated discrepancy, which is measured to be 0.28%. And you see here the dominating uncertainty is the systematic one, coming from this charge asymmetry effect. And before concluding, let me just mention another measurement we were able to perform on BEL2 2019 data, exploiting a similar technique, which is the measurement of the fake rate, for which we mean the probability to reconstruct a fake track, which may come from the random combination of mainly beam-induced background hits, but also from low momentum particles that occur inside the detector without pin merge. It's what we call the clone tracks. Here we exploit the similar tag and probe technique, but we fully reconstruct a 3x1 prong event by asking for 4 charge tracks in the event, and then we look for the 5th one that has to be a fake since it doesn't conserve charge. And again, we count the events where we find the 5th track and the events where the 5th track is not found, and then we compute the fake rate as the ratio of the N5 events to the total reconstructed events. In this case, since we can reconstruct the full event, we can exploit event shape variables to improve signal purity, which is measured on simulation and used to scale data yields before computing this fake rate, which is measured to be 0.97%. And here the uncertainty is just statistical, since we just started to evaluate the systematic uncertainty for this measurement. And this brings me already to my conclusion. So let me summarize here that BEL2 was successfully taking data since the beginning of phase 3 and during all the 2020 run periods. So on the almost 9 inverse femtobarn of data that we collected during 2019, we were able to devise a strategy to measure the track reconstruction efficiency convoluted with the acceptance of the detector by analyzing the 3x1 prong tau pair decays. And based on this measured discrepancy, we could provide analysts prescription on how to assess systematic uncertainties for their analysis for tracks dealing with transverse momentum in the range between 0.2 and 3.5 GeV/C. And with an analog technique, we could also measure the fake rate in BEL2 data, which is found to be consistent with what we expected from our simulation. So that's basically all I wanted to tell you, and thank you for your attention.
Thank you, Laura, for the very clear presentation. I'm afraid that we are running out of time. So is there quick questions to Laura? So maybe I have one in slide 13. I've seen about your systematics that combining the samples, you can already reduce these systematic effects a little bit.
Yeah, that's true. And another in from the fact that the systematic is mainly dominated by this charge dependence. So when we combine all the samples, we are somehow also average on this effect, which is mitigated then.
Ah, okay, I see. Any other comment or questions? So if not, thank you, Laura, again. And now we come to our last talk of this session. It's Cyril Prats from DAISY about the B lifetimes, again at Bell 2.
Hello, can you hear me?
Yes, and we also can see you.
Right, sharing the slides. Sorry. Yes, do you see the slides?
Yes.
Perfect. Thank you very much. So hello, everyone. I'm here today to talk to you about a measurement of the B meson lifetime at Bell 2. Most of the things that I will cover today are summarized in our conference note that you can find on arXiv. So after a short introduction, I will explain you the measurement strategy that we used and then the different components that enter into our probability density model, a quick note on the systematic studies, and finally the results that we obtained. So sorry if I repeat some information already said by the previous speakers, but in case people are joining now. The Bell 2 detector is located along the Super KP accelerator, which is a E+ E- collider working at an energy of 10.6 GeV, which is close to the mass of the Upsilon 4s resonance. And we use this resonance because we know that it decays nearly all the time in a pair of B mesons. That's the reason why we call this a B factory. And you can see here the roadmap for the next years, and we still our goal is still to reach an integrated luminosity of about 50 inverse femtobarn by the beginning of next decade. So here you have a side view of the Bell 2 detector, and for the measurement that I present today, the tracking system is absolutely crucial. So it's made of a vertex detector and a drift chamber, the CDC, and the vertex detector is made of 2 layers of silicon pixel detectors and 4 layers here, the SVD of silicon strip detectors. And as already mentioned, the second layer of the BXD is not yet fully installed, but it will be around 2022. And around that, we have one calorimeter and a few modules for particle identification. So for this measurement, we used the 2019 Bell 2 data, so an integrated luminosity of 8.7 inverse femtobarn. And one important note for this study is that Bell 2 has a smaller boost compared to Bell. So we have to compensate. So the boost of Bell 2 is about 0.28 to be compared with 0.42 for Bell. We compensate with a better impact parameter resolution of about a factor of about 1.522, thanks to this pixel detector. And of course, a good vertex separation is crucial for this kind of studies. If you are interested in the CP violation results, please have a look at the presentation by Nikara Ruth at the following link. And just to illustrate the capabilities of the Bell 2 tracking, here you see a measurement of the X sites of the beam spot. This is given in micrometers as a function of the run number. So in red, you have what we have from the machine parameters, so from the beam optics. And in black, you have a measurement made from the tracking system of Bell 2. And you can see that we can really measure these beam spot sites only with the tracking of Bell 2. So to enter in more details of the measurement strategy, we reconstruct the hadronic decays of B0 meson, the signal side. Here we call it like this. And the other B vertex is reconstructed from the remaining tracks in the event, so here called the rest of event tracks. And we use the fact that the B mesons are produced nearly at rest in the ε4s frame because of their mass. So we can neglect the flight distance and estimate the decay time difference from the vertex separation that we measure here and correcting for the boost. And to give you an idea, delta Z is of the order of 100 micrometers. And then a naive model for this decay time difference is simply given by taking the joint probability. And this would be a function without taking into account the resolution of the detector. Here I'm listing the different decays that we reconstruct. So it's B to D plus hadron, and then also the list of the D decays that we reconstruct. And for the constraints that we impose, we use two very nice variables that we have at Bell 2 because of our knowledge of the full event. So you have the beam constraint mass, which is built from the energy of the beam and the momentum of the beam meson, and the energy difference between the energy of the beam meson and the energy of the beam in the center of mass frame. So here I'm showing the probability density model that we use for this decay time difference. So it's made of three components: the signal, which is simply our naive model convoluted with a resolution density that is taken to be the sum of three Gaussians. Then we have the B background density, so other B meson decays that are wrongly reconstructed. So we take the same functional as the one for the signal, but this time instead of the decay time of the lifetime of the B meson, we take an effective lifetime for these B mesons. And finally, a continuum density that is again taken as the sum of three Gaussians. So in the next slide, I will show you how we extract the different parameters that enter into this function. So to extract the yields, we do a 2D fit on the unbeamed beam constraint mass and this energy difference that you can see here for data. And from this 2D fit, we can extract the number of signal, BB bar, and continuum events. Then for the continuum shape, we look into the sidebands of our sideband events that are defined with respect to the beam constraint mass and the energy difference. Here you can see this time difference in simulation and in data. And here we extract most of the parameters from simulation, but to take into account a difference between simulation and data, the common mean and variance are taken from data. For the resolution this time, we look into the delta T residual. So what we do is that we compare the time difference after reconstruction in simulation with the true time difference that we know because it's simulation. And from that, we can extract the resolution parameters. And so once the resolution function is fixed, then we can measure the effective lifetime for the PB bar background. Sorry. Yeah. After that, we have, I'm listing here the list of the sources of systematic uncertainties that are considered. So we expect, of course, some systematic from the fit parameterization. So we reproduce the fit on 10,000 simulated bootstrap samples, which gave us a systematic of about 0.05 picoseconds. Also, we checked what happens when this effective lifetime is left free. And finally, in data, we rely on calibration and alignment constants. So we reproduce the full study on a subsample to check the difference with the different calibration and alignment constants. So at the end, taking all of this into account, we can fit this time difference for all the B to D hadron of the selected decay candidates. So you can see here, actually, it's the same plot once in a log scale and once in a linear scale. And in these fits, the only three parameters are the lifetime of the B meson and the main, mean, and variance of the resolution function. And this is the results that we obtained, 1.48 picoseconds. And you can see here that given the sample that we used, we are highly dominated by the statistical uncertainty. So as a conclusion, we measured the B0 lifetime with the BEL2 data, giving this result, which is in good agreement with the world average. Of course, for now, we are still dominated by the statistic uncertainty, but this measurement assesses the accuracy of vertex fitting tools, time resolution modeling, and detector alignment at BEL2, because of course, if you don't control your alignment, you have no chance to measure such a quantity. And once again, the conference note is available online. And I would highly recommend you, if it's not done, to have a look at a talk by Julia on a D0 lifetime measurement, which was done with a larger data sample and found that time resolution 2 times better than what was observed at Bell and Baba. Thank you very much.
Thank you, Cyril, for this nice presentation. So are there questions to Cyril? If not, maybe I can ask you about your slide 10.
Yes.
Where you were talking about the extraction of the parameters, and some come from simulation, some from data. So could you, maybe you mentioned, but I missed, is use of data for extracting parameters limited by statistics essentially, or there is another reason why you don't extract all the parameters from the data?
Oh, yeah, actually, so actually, you can already see on this plot that the statistic here we are really dominated by the statistic. I guess that with a larger sample we could be more precise in our choices.
Okay. Yeah, that was my guess. So yeah, I was right. Okay. Any other question to Cyril? So if not, we thank you for the nice presentation, and we thank all the speakers of the session, of today's session. And we close now because the poster session is going to start immediately after this one. So I let Jerry comment on the timing. I don't know if we have 5 minutes of stop between the two.
First of all, thank you very much for this very nice session. It was a dense program, but wonderful presentations. Thanks also, Stefania, for very nice sharing, good work. Okay, I think that now we should almost immediately start with the posters, but I think that let's say 5 minutes as a break would be nice. So let's say that we can start in 1:50 p.m. Prague time, which is like in 6 minutes. I think that the posters will be presented in this Zoom meeting room. But now I would like to ask the Martin, who is the Zoom technical assistant, how it will be with the recording, because now the recording should be stopped. And
yeah, I will stop the recording, and we will change with another person, another chair of this session. So I need this 5 minutes for the conversion of the recording.
Okay, but my question is, when you will leave the meeting, the conversion will start, so we can stay in the meeting.
Yeah, you can stay.
Okay, perfect. So yeah, it is not necessary to go anywhere. Everybody is, of course, heartily invited to this poster session. More people, of course, better discussion. So please stay here.